Uh, it's live now. I think we can start now.
Cool.
Okay.
Okay.
Can we start?
Warren, just give me a second.
Okay.
I'm
Come on, Simon.
Simon, will you be introducing more? So there. Oh, it's empty.
It's a media room. It should be. Yes,
Okay.
it's a good idea to repost.
I
For
think
those people who are just arriving, we're basically going to be using the resources from this website called wiki.bdNOG13.net, and you can get access to them through that link that was posted.
Warren, I think we can start.
Excellent.
Zubair. Okay, guys. Thank you for joining. I think we have almost 40 people right now, so we can start right now. So, good morning, everyone. সবাইকে শুভ সকাল। আজকে আমাদের bdNOG-এর দ্বিতীয় টিউটোরিয়াল দিন। আমরা খুব সুন্দর আজকে একটা টিউটোরিয়াল শিখবো, সেটা হচ্ছে সেগমেন্ট রাউটিং। এবং আমাদের এখানে তিনজন খুব ভালো ট্রেনার আছে, দুইজন এপনিকের কর্মচারী এবং একজন এপনিকের কমিউনিটি ট্রেনার। The first one we have Tashi Funshu. He is the training development manager. He by origin he is from Bhutan, but he loves Bangladesh, but unfortunately he is living in Australia. The second one we have Warren Finch, very senior guy and very good trainer. I had a very good chance to work with him a long time back. Very much expert on Vegemite.
Yeah. You still don't
one,
like Vegemite. I haven't done my job right.
The third one is Zubair Khan. He's from Bangladesh. His day job is in Fiber at Home, and he's working as a Ethnic City for a long time. So good trio, I should say. And let's start. Warren, Tashi, and Zubair. The floor is yours.
Thank you. So we did start before, so I'll just go back to this slide here. My name's Warren Finch, as Simon already introduced me. So what we're going to be talking about in the next 4 hours or so is an overview of the software-defined networking framework. So that's in a nutshell. And where does segment routing fit into that? And because we don't know what your background is, we want to give an overview of MPLS. So we're going to do a recap of that so you understand how you would normally direct traffic through your network. Then we start getting into the nitty-gritty of segment routing, what the architecture is, talking about some of the RFCs and the documentation that the vendors are doing to try and build up this uptake for segment routing, talking about MPLS in the data plane and the border gateway protocol, egress peering engineering to make sure that it works the way that we want, and then maybe some of the LDP into working if time permits. What we may do, instead of just going straight down the theory and then breaking out and doing the practical, similar to what we've got here in the website, we may swap around some of this. So start doing the theory, and then to reiterate that theory, we'll start the prac, doing a lab. If you've done some of the lab, it then makes it easier for it to relate that to the theory. And that's the way I tend to do things from there. For those people who weren't at the start of the presentation, there's a link here called SR Lab on Academy. If you can open up that link and create yourself an account, if you haven't already got an account, you just go up to the top, log in, and then under the login, you've got this register option there. It's a good idea that for that APNIC Academy account, if you've got a My APNIC portal account, make sure that you create a separate account. You should always have an account for management or doing anything to do with changes to your assets that you have. And then one for learning is going to be completely separate. So think about that obscurity. and the security that you have with that. So I'll hand it over to Tashi. He wants to talk about the architectural framework of SDN. So
Thank you. Thank you, Warren. I'll spend about 5 to 10 minutes on the slides, hand it back to Warren and Zubair. But before we even look into, can everyone hear me okay?
I can't.
Zubair bhai, you can hear me okay?
Yeah, Tashi.
Cool. So with that, let me annotate, right? Is that the pen? All right. So what is this SDN thing, right? Many people have many different definitions of what SDN is. Some have very radical ideas. If you look at OpenFlow standard, they're saying, oh, let's do a complete decoupling of control elements out of your box, keep your data planes very dumb, centralize all your intelligence in a central server somewhere. But what that does not factor in, that's a beautiful idea if you can do it, right? But the reality is you can't have a flag day on the internet. You can't shut down the internet and tell your users that, hey, I'll come back to you 6 months from now. I'm going to implement something nice and beautiful. So there is no way you can have those kind of a flag day where you can shut down your network completely to allow you to implement something new. So that OpenFlows, that idea of a complete decoupling of your control plane, and your data plane doesn't really make sense, because you end up with dumb data plane, the actual physical infrastructure, intelligence sits somewhere. What happens if I lose connectivity with my intelligence? All of a sudden a packet comes, the box doesn't know what to do because the intelligence has disappeared, and then you bring your whole network down to its knees, right? So, but you have to give credit to those researchers from Stanford who started the OpenFlow project, because they gave a couple of ideas. One idea is not new, which is decoupling your control plane, your control elements from your data path elements, decouple them. But what they did is they did one thing which is great, because this idea is not new. It was always there. Those days, those of us who work on transmission, Simon has worked on transmission, Zubair, Warren, Dave, all of us, we used to have those muxes. You have a synthesis card, you have the line cards, tributary cards. That is a decoupling of control and data plane elements. So it was always done, but it was done in a very proprietary manner, not an open standard manner. It was done in a proprietary manner. So my question is, did they propose anything new? Not really. This is not a new idea, decoupling of your control plane and data plane. But what is new is this concept of, if you look at the current way we do on routers or multiplexers or any boxes, DWDM boxes, you see there is decoupling of this control and data plane. But what you also see is this 1:1 association, right? What do I mean by 1:1? Which means one control plane controls one data plane. So the classic or the traditional way of doing things is we have 1:1 association. You have a control element that talks to one data path element. But what the OpenFlow guys proposed is great. They said, hey, how do I get a whiteboard here?
W. Just press W.
All right. So now what the OpenFlow guys proposed, one thing that stands out compared to others is they said, okay, here is your box. Keep only the data path elements there. Let me extract out the control path elements too and put it on, let's say, a server externally. But what they said is, currently, this is still 1:1 association, right? You haven't done any magic. We used to always do this. But what they proposed is, now the fact that you are able to separate your control functions from your data path function means, what is to stop me from doing from a 1:1 correspondence to a 1:n correspondence? What do I mean by that? That means 1:1 is only one control plane managing only one data plane. How about multiple data planes? Data plane, data plane, data plane, and all of those data planes are now controlled from one central control element. That becomes what people generally tend to call it as the SDN controllers. The idea is I have one control function through which I can now control the dumb devices down there, which are my data planes. And we now are moving to what's called a 1:n correspondence. And this is very powerful concept, right? That OpenFlow researchers from Stanford University proposed. Why is this powerful? Because all of a sudden, I have now the ability, if I add some layer of color, something else. There you go. So what this allows now is I have a central single control plane example in this example. What this means is if I can manage more than n number of data planes downstairs, that means it allows me to now add this layer of abstraction here, a layer of abstraction. Whoa, a layer of abstraction here, which means now I'm the controller. I'm sitting centrally here. I look at my data plane, my data path. My data path could be Cisco gears, they could be Huawei gears, they could be Juniper gears, they could be any vendor gear. Doesn't matter. From the control plane's perspective, I see them all as data plane, the data path elements. But if I add one layer of abstraction here, where all of a sudden my forwarding, which is my data path elements that are on the actual physical devices, can I abstract them? And what kind of abstraction did they propose? They proposed abstractions called flow tables, right? All of a sudden, all my data plane, whether it's Huawei or whether it's Cisco or whether it's Juniper, all I see is they all look the same to me. I abstract them as flow tables, which means now it's so easy for a central server to have one common instruction that applies to all of this, my physical devices. Because currently, think about it currently, everyone. How do you manage or interact with your device? Do you have any open interface? Or do you interact with your device through a very proprietary or closed interface? Anyone? Before I proceed, I want some response. My question is, how do you interact with your devices today? Do you interact through a closed interface? Or do you interact through an open standard interface with your device? Anyone? Raise your hand or type it in the chat. Can anyone tell me how you interact with your device today? Zubair bhai, I can't see anything.
Yeah, guys, please try to interact. So
Oh.
this session becomes very useful to you.
Saiful says it's a closed interface. Saiful, you're right. Your CLI, right? You
Thanks.
look at your Cisco CLI or you look at your Juniper CLI, Huawei CLI. These are very closed proprietary interfaces, right? So what is the most common open interface we use at the moment? Traditionally? Anyone? There is still an open interface through which we interact with our devices. Every device speaks that. Every vendor box speaks that. There's only one open interface currently, traditionally, I mean. What is that? Closed interface? Yes, your CLIs and all those are closed interfaces, right? What's that open interface? There's still one open interface that allows us to interact with any vendor device. Silence, all right. You guys know SNMP? SNMP is an open interface. Yep, Dave, thank you, SNMP. Whether it's Cisco or Juniper or Huawei, they all need to support that. That's the only open interface we have in the traditional way of doing networking, right? So this motivation is very important to understand how the OpenFlow from Stanford University, how their research is now shaping how the networking world wants to do things. This concept of abstraction, this concept of decoupling control elements away from your data path elements, centralizing them in a central server, moving away from this 1:1 correspondence to what is now a 1:n correspondence, where you have one controller sitting somewhere that can now talk to that many data path elements down there in my network. Or from an OpenFlow perspective, all I see my network is flow tables, flow tables, flow tables. I don't see them as Cisco box. I don't see them as Juniper box, which means from a management point of view, whether you are orchestrating a new node or whether you are reconfiguring or managing any of those nodes, one template is enough for me to talk to any of my devices instead of me maintaining a separate template for Cisco, separate template for Juniper, you know? So this concept of abstraction is very, very important, right? OpenFlow's way of abstraction is using flow tables, and the interface that OpenFlow has to interact between the controller and the data path element is what we call the OpenFlow protocol. So OpenFlow is nothing but an open interface through which the controller can talk down to its flow tables or data path elements. Clear, everyone? Before I jump back to
Really clear as Vegemite.
so I do escape, I'm back. And how do I erase that? Shift E.
I normally do it this way.
Erase all. So now coming back to this slide, right? Coming back to this framework, this is very important to understand, right? So this is what I was saying earlier, this OpenFlow wanting to us to completely decouple, take away all intelligence away from the box means what? That means you end up with a very dumb network, which means things could really go bad if something happens to your controller because there is no intelligence in the box. So the industry said, hey, OpenFlow, great idea. You're teaching us how to abstract things. You're teaching us how to create open interfaces. You're allowing us this new concept of agility, new concept of programmability. But in reality, I don't necessarily want to abstract. I don't necessarily want to decouple all my control elements away from my box, because currently look at the traditional boxes we have. We have distributed intelligence. Every node is capable of making its own decision currently. If you look at our network, let's say you have a network, I have a network, I have my router spread across the network. Each and every router is capable of making its own decision. So we call that distributed intelligence, right? All of a sudden, OpenFlow is asking us to completely go the opposite way from a completely distributed intelligence system to go a central intelligence and very dumb devices. But when things go wrong, there is no fallback. Whereas if I leave some control elements still down there, if I leave some control elements or intelligence still down there in my box, if something happens to my controllers, for some reason, if something happens to my controller, the fallback is its own local intelligence. At least it can forward packets. At least it can receive read packets and forward packets if you still leave some control elements down there. Because the industry went, hey, we can't undo what we did and learned in last 20 years just because you have this beautiful idea to decouple everything. So that's why OpenFlow works really great in a campus. It works really great in a small data center. But outside of that, the moment you take it to a ISP style of network where you have regional networks that are spread across regions or geography, it becomes really challenging to adopt the OpenFlow concept, because OpenFlow's biggest problem was its topology discovery was using a link layer discovery protocol, a LLDP protocol. So imagine if I have my network across 7 or 8 countries and LLDP is my communication between my device and my controller. It's not going to work. That kind of topology discovery system just doesn't make sense. It won't scale outside of an equipment room or outside of a campus. It's very difficult to imagine that. And hence, just a quick disclaimer, Paresh Bhai, who is the CTO of Nokia, helped develop this content for us, right? And he is aware of so many other SDN architectural framework, and he feels this final framework is a very practical framework which people can adopt. And I'll discuss about those. Erase all. So with that concept that OpenFlow and others have, here is what a practical SDN architectural framework looks like. What do you have? First, let's talk the controller. First, you have your control elements here in what's called a controller. You have decoupled those key control elements that you can decouple, but you haven't gone crazy and you haven't taken out your IGPs like your OSPFs or ISIS. You haven't taken them away from the box. They're still down there, right? But what you have taken away is you have taken away certain functions. Now let's have a look at this. Let's start from here. Now, configuration or config management function that has been taken away from the box and put up there in the controller. And the way that your configuration management interacts with your box is through open interfaces here, right? OpenFlow, I already discussed this. It's an open interface through which the controller can talk to your data path elements. And OpenFlow is really good if you want to inject a new flow in your flow table or modify a flow in your flow table or delete a flow in your flow table. You could do that by relying on OpenFlow as an interface. But the problem with that is your box needs to support OpenFlow. We call them OpenFlow enabled devices, right? These are hybrid devices that can do normal switching, but they can also listen on OpenFlow interfaces. So you need that to be supported. Our classic open interface is SNMP. Everyone knows how SNMP works. Every device is a MIB tree, and then you query through your SNMP protocol, either to look at specific branches, which are your OIDs in the box out of the MIB, right? But how many of us actually configure our devices through a SNMP write function? Not many of us, right? So it's clunky, and it never gives you a real-time indication of what's happening. Oh, 5 minutes later, you receive an alert saying that, hey, your traffic looks weird. You try to make changes. By the time your changes come, the traffic pattern has already changed, right? So SNMP is that kind of a thing. And just last week, when Papubai, Fakrul, and Warren were teaching Tonga NMM, I tried to make a joke there saying that, hey, if your pilot in the airplane cockpit receives his telemetry data, not through telemetry, but through SNMP, will you fly? By the time pilot reacts, it's a 5 minutes delayed information that has come to me. Fall down to this altitude. You haven't fallen down because you received the information 5 minutes late. I don't want to fly in those kind of planes, right? So that's your SNMP. Now, lately, in the last 4 or 5 years, we are seeing some standardization, right? People are saying for config management of your devices, can we talk through an open interface called a network configuration protocol, netconf? It's an interface to interact with your devices. And it really relies on an RPC paradigm. It's a remote procedure call paradigm, right? Something as simple as, let's say you're the controller, you want to talk to your device. You send a remote procedure call. You say, hey, give me this. The device is supposed to give you that. And generally, you can do this either in an XML format, right? Where controller down, you might have, what's the XML syntax? Open XML instructions, 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 XML close, right? You could be having instructions there, goes to the device gives you back a response, again, in an XML syntax, right? So it's a remote procedure call. So it's still an open interface. But for your netconf to work, you see here something called Yang, right? This fancy name, this is not yin and yang, right? Yang stands for yet another next generation, right? Yet another next generation. Even Yang models, there are 101 models. IETF is trying to standardize them through IETF Yang. Other vendors, they use SDOs, might be doing their own Yang model. But what does Yang help us with? Let's focus on the Yang bit. Remember, I was talking earlier about this need to abstract. What is abstraction? I've already given you an example. Abstraction means what? Whether my network has Juniper gears or Cisco gears or Huawei gears, any multi-vendor gear, can I have a layer of abstraction on top of that through which I see them all as same from an interaction point of view? So Yang is such a modeling language, right? It helps me do that modeling, right? Yang helps me model my different devices, data path elements into a nice tree, right? Yang, you can model, it's like a template that you're trying to build, right? Oh, my interface is maybe, let's standardize how you represent the interface. Let's standardize let's standardize how you represent the protocol if it's BGP, right? Let's standardize what CPU should look like. Let's standardize my interaction with the memory. So you have this kind of a model, and then you have this tree, you have a child, you have subchild, you have the relationship between the parent and the child, because within that interface, if this is interface, under the interface, what is the bandwidth? What kind of policy shapers do you have that are tied to that interface? You could try and represent all of them in a nice standard template. So that looks like it's an abstraction of my physical device. I could have Cisco gear, I could have Juniper gear, I could have Nokia gear, Huawei gear, any gear. If they can be modeled using the Yang model, then they will all look the same to me from my side, the controller side, wherever I'm sitting. They all look same to me thanks to modeling tools like Yang. Now that means I can interact with every device in my network using the same communication, right? Through the netcon protocol, right? So that's on the config management function. Now, from a resource management point of view, IP fix, IP flow information export, right? This is just a framework. This is based on this is based on your Cisco's this is based on your Cisco's flows, right? It depends on that version 9. It is a copy of version 9, but this they are trying to standardize it by saying how should a flow exporter and a flow collector, what is the protocol? How should they behave? So IPFix kind of tries to define that standard communication between a flow exporter and a flow collector that sits there. That's for resource management, because remember what I said, you have pulled out some intelligence from the box. The controller is sitting here. For controller to make any good decision, it needs to know what is already utilized, what is free down there. Hence, that resource utilization information can come through things like IPFix, right?
The telemetry that you need to fly the plane.
That you need to fly the plane, exactly. Now comes forces. Forces, not so much development in this area. Forces was forwarding and control elements working together. So you have your control element here, you have your forwarding element here. It kind of defines the standard between how a forwarding and a control plane should interact. Again, there's not much development going on there. That's on the resource management side. Now let's talk topology discovery before I come back to traffic engineering. Now, remember what I said, your controller is sitting here. You have all these devices that are controlled from a central controller. But for the controller to make the right decision, how do I know that the link from router 1 to router 2 is exhausted or not? How do I even know that there is a link between router 1 and router 2? I need that topological information. If I'm the controller, the smartest god out there in my network, I first need to know how my network is physically connected before I can push any instructions back to my network. And for that, what do we need? We need topology discovery. Remember what I said about OpenFlow. OpenFlow was using LLDP, still uses LLDP as a topology discovery, doesn't work, doesn't scale for examples I gave earlier. Hence, IETF has gone ahead and modified our BGP. And this is where Zubair, Dave, Warren, Papuba is also online. Our BGP is now becoming like a donkey protocol. Modify it, carry this, carry that. So this is beautiful, right? How does BGP LS work? You have BGP, right? Normally BGP only carries what? BGP doesn't carry topological information normally. BGP carries your routes, along with that, your path attributes, right? But what else does it carry? It doesn't carry much, right? But what they're trying to do with this is link state information, your OSPF information, your ISIs. Link state is beautiful because the fact that when I look at my link state database, that link state database gives me a picture of how I am connected with the rest of my network, right? Normally OSPF or ISIS, when we look at our LSDB, that means that is my full picture of the network. That link state information, you carry it in BGP as a separate address family, AFI, and then all you need now is you have this many devices. Let's say you have 1 million routers in your network. Doesn't mean you need to do BGP LS with every device in your network, right? You might already be having iBGP with all your other devices. You already have IGP running ISIS or OSPF, right? Every router has that topological view. All you need is any one node in your network to feed that topological information to your controller through a BGP link state protocol. So you carry that topological link state information inside your BGP as a separate address family, and you have a BGP session between that node, one of those nodes in your network, and your controller. That's how your controller knows how your network is connected. Now that I have view of the topology, I can now make any changes I want in the network because I know how the network is connected, right? So that is what BGP LS is all about, right? For topology discovery. Now let's look at traffic engineering. We are also saying let's extract the traffic engineering function out, right? You already might be doing some traditional traffic engineering tools like RSVPTE, right? But for your control element to now interact down with your data path element, we need some new open interfaces or open protocols again. And for that, IETF has again defined what's called the path computation element protocol, right? It's a path computation element protocol. Open interface allows any controller to talk to any of your data path elements, right? But that means I need a path computation client capability sitting on my box so that I can push those instructions down to the box, right? And one of that technology is segment routing, which Warren will cover. Segment routing allows you to engineer traffic within your backbone. And Warren will go into details about how you can manipulate that. That's just one function that you are trying to manipulate. Today, we will teach you only one function. Other one are examples like route selection and failover. Normally, how do you manipulate your forwarding behavior in a network? There's no other way, right? You have to manipulate the routing states to manipulate the forwarding state because your fib is generally learned from your rib. Whereas into the routing system, I2RS, it's a new protocol. It allows me to inject on-demand states. Let's say something has happened quickly in my network. I need to react to it. I need to be able to inject those on-demand states into my routing plane so that it manipulates to manipulate my rib so that it manipulates my fib, my forwarding behavior, right? So this is what a practical SDN framework looks like. So as you can see from this explanation, there is no one thing that we can call SDN, right? SDN is just this, what a journalist, I think somewhere when they were reporting on the Stanford University work, they just coined it as software-defined networking. But you see, it's more a framework, it's more a thought process change, but nothing too majorly. Everything is all about open interfacing. Everything is all about abstraction, right? So based on this, what everyone should know is for your controller to interact with your devices, you need a layer of abstraction, right? Those abstractions are provided by tools, modeling languages like Yang, right? And hence, this open interfaces that we interact down, they are generally called southbound interfaces, meaning south of the controller down to the devices. But that is not the ultimate aim of SDN or this new notion of programmability. The new notion of programmability is your network services here. You have network services sitting there. What are your network services? Could be your customer portals, right? Your self-service customer portals, could be your OSS, BSS systems where customers can submit the order. Hey, I want a VPN circuit from here to there. It comes to your network service, a portal example. That portal should now be able to push that instruction down to your controller and say, hey, provision this service. But how can that network service understand what your network looks like? It doesn't have to know the nitty-gritty physical details. All it needs is an abstracted view. All it needs is an abstracted view of your network that the controller can present up to your network services like your self-service portals. Based on that view, they will say, all right, man, steer traffic from that link to this link. They will send that instruction down, and even that they can come through RESTconf, a web query coming down, a RESTful query coming down, or they can still do it through netconf, or they can do it through XMPP. That comes to your controller. Your controller reads that instruction. It makes changes to your network without human intervention.
So who attended Buckball session yesterday? If you want to click on yes.
Warren is asking a question.
So who attended the session yesterday on the modern programmability? Because you would have been exposed to the RESTconf, netconf.
Did anyone attend Papuvai's NMM 2.0?
If you go to the reactions and click on the yes, which is the green tick, or raise your hand.
If you have attended Papuvai's session yesterday, please give us okay. I can see one. Yep, I can see you, Alambai, Benozer, two, Moin Uddin Bhai. Thank you.
So you can all give us a talk about it now.
Yeah. So that is that, right? So you see, that's why we call this, I mean, like you can't really define and say this is SDN, right? It's a framework, basically. It's a framework. And as you can see, the problem with centralizing control functions up there in a central server means you need resiliency also, right? What if this controller goes down? Then my network goes down too. That's why you also need this concept of east-west interface where you could have multiple controllers that talk to each other. Now, the problem with that is then you need to make sure both the controllers are perfectly in sync. Right. So you keep adding that extra layer of complexity because the moment I have two controllers, I want to make sure they are both in sync so that one instruction that one pushes down to my network doesn't get undone by the second controller sending a paradoxical instruction down where one says do this, the other one says don't do that, do that. Hence why there is also standardization happening at the east-west side, controller to controller also. Right. So with that overview, I'm going to hand it back to Warren Bhai and Zubair Bhai. Oh, Zubair Bhai, with this, I'll hand over to you. So just a sec, let me first erase all this. Next slide. So with that concepts, I'll let Warren explain segment routing this in a nutshell. But what's important for you guys to realize is that the framework, right? There's no one way of doing and say, oh, I'm SDN network, right? All right, Warren son.
So in regards to what we're going to be focusing on later today is segment routing. So we saw where it was in the framework here in the networking devices, but the idea behind it is that you're going to start engineering your traffic so that way the source determines where the packet goes to. Traditionally, it's going to be the information from your destination that will determine how to send your packets. Or if you do the MPLS, where you can do labeling of your information, you can then send it a certain way that way. This is where the actual source will create those labels and encode that sequence through the segments or give instructions along the way. And so the idea then is that you can reduce your network state and have this path computational element in there as well. So you've got the centralized controller that knows where everything is connected to and how the best path is, and you can make decisions from that central location. Just to recap the MPLS, I'm going to hand over to Zubair and let you have the floor. Did you want me to continue sharing the slides and you just tell me when you want to proceed to the next slide?
It would be better if I share my screen.
Okay, then I'll stop my share. And hand it over to you.
Yeah.
I'll just turn off my video while you're presenting.
Okay. So are you getting my screen?
Yep.
My voice is okay?
Yes.
Okay then. So should be.
While we're setting that up, does anyone have any questions?
So for the Q&A is empty, so I don't see any questions.
That's okay. We'll move on.
Yeah. Okay. So here we go. As you guys have seen so far, the concept of SDN and the concept, the very basic concept of segment routing has been explained by Tashiva and Warren. So if you want to get involved deeply with segment routing, the first thing you need to know is a little something about MPLS, because the segment routing, the working procedure of segment routing is actually focused and based on the working principle or architecture of MPLS, right? So what is MPLS? It is named as multi-protocol level switching. We use it to serve a number of types of services altogether within with the help of a single infrastructure. So it uses tunneling protocol within different tunnel. It serves different services. Each service is termed as a forwarding equivalent class or FEC with a level value of 20 bit. And whenever any service comes into network ingress node, it is number of types of services altogether with the help of a single infrastructure. So it uses tunneling protocol within channel different services. Each service is termed as a forwarding equivalent class or FEC. Sorry.
The sound went a bit weird then.
Yeah. So I've muted. Okay, going back. So as I said, whenever whenever the packet comes into the ingress node of MPLS network, it is assigned. It is or I would rather say it is classified into FEC, and each FEC is assigned the level, and all the intermediate hops in the infrastructure, they just keep swapping the levels and take the packet forward, right? So this is pretty much straightforward what MPLS, how MPLS works. So whenever we're talking MPLS, we're actually talking about decoupling, routing, and forwarding. In our traditional routing working principle, we know that whenever packet comes into your router, it looks up into the packet, in it looks into the destination, and it associate with the next hop and the interface via which the destination can be achievable, and it forwards the packet, right? That is how it happens. So all the decisions are based on the routing, which are routing protocols which are running into your router or into your network, right? So whenever you're doing MPLS, your packets are getting labels, and all the intermediate routers, all the interconnected routers, they're actually just swapping the levels. Your routing is creating the path, your IGP is creating the path and installing the path according to the decision of the IGP. And the packet which is being forwarded based on the decision of that IGP actually is moving forward by swapping level by all the intermediate routers, right? That is how it happens in MPLS, right? So if you look closely how MPLS work, there is a concept of level edge router and a level switch router, right? So whenever a simple packet comes into a level edge router, this router insert MPLS shim header in between the data link layer and IP layer of its overhead. So in that MPLS SIM header, you can find a level value which is a volume of 20 bits. So you have around a million of levels to play around with. So whenever the packet enters into your MPLS domain, the activity or the responsibility of LER or level edge router is to insert that MPLS shim header into that packet, right? And whenever the packet gets the MPLS shim header, it moves forward to the next immediate router in your MPLS domain, which is called actually level switch router (LSR), right? What it does, it swaps the it swaps the level from the previous one to its own locally generated one, and it sends the packet forward, right? So as I try to describe the mode of operations, there are actually three you need to know. The first one is push, what the LER does. So as I said, the LER push the MPLS shim header into a packet, right, and make it a labeled packet. So this inserting the MPLS shim header into the packet is actually called push, and the second one is swap. Swap is the activity of LSR, right? Whenever it gets a label packet from an ALER or from its previous LSR, it checks the label and it swaps the label to move it forward to the next LSR or ALER, right? And the last one is pop. So the pop is actually removing this MPLS shim header or removing the label and take the packet to its original state, and it happens in the egress LER where your MPLS domain is ended and you're handing over the packet to your client, right? So in that LER, the labels are removed, and this removal of label is actually called pop. So these three basic information of MPLS label operations are required to know when Warren will move forward to explain how segment routing works. You will hear these words again and again. So keep this in your mind. So if we try to come up with a comparison how the architecture looks between our ordinary routing domain and MPLS routing domain, it should look like this, right? So just forget about the orange one. First, focus on the green side. So what happens? Incoming IP packets. So your control plane is keeping all the information in a routing information base, right? And all these informations are being inserted into the RIB based on the IP routing protocols that your network is running, right? And these protocols actually decide what are the best decisions will be to forward and form a FIB, which is handled by the data plane. So all the incoming IP packets, they are actually maintaining the FIB and acting accordingly, right? So here, if you look on the green side, everything is happening in our traditional routing with our traditional routing idea, right? Now, if you focus on the orange side, so the difference you'll see that we are talking about levels now, right? So in the orange side, there are incoming labeled packet, right? So your control plane is having the label information base, which we call lib, and these level information based is actually made based on the decision of level distribution protocols, LDP, right? And the from the level information based, with the help of LDP, your routing domain or your data plane gets the level forwarding information base, or we call LFIB, right? So all the incoming level packets are acting according to the LFIB. So this is the basic idea. This is the basic idea of the MPLS architecture. Everything is going just like our traditional routing architecture, but here we're talking about actually labels, right? So now I would go through some topological idea. Right here, as you can see, a small MPLS network. We have two LER and we have around six LSR. The two LER, the first one is we are mentioning as ILER, or ingress level edge router. So what happens when an IP packet comes into ILER? It does a specific operation. Can anyone tell me what operation it does in the chat? So what does an ILER do whenever a packet comes to it? Can anyone tell me in the chat? I just went through the operations. Push level, exactly. Thank you, Mahbubur. Yes. So ILER, the activity of ILER is to push the level into the packet, right? So it is also written here, the MPLS router that pushes MPLS level is called ILER, right? And then when the packet has got a level, it moves forward to its next LSR, which we call a level switch router, right? So in the level switch router, the action. So what is the action a level switch router does on a level packet? Can anyone share? Swap. Yes, exactly. Bang on the target. Yes, swap. And then this is how the packet moves forward, and whenever it is going to leave your MPLS network, the last router or the last node, which we call egress level router or ELER, there is another operation that router does. Yes, pop level. It pops the level and it take the packet into its original form, right? Exactly. Thank you guys for participating and making it international session. Thank you for that. Our next slide actually explain the same idea but with the VPN node type. So here we have provider edge router and provider router. The concept is basically same when LER with the concept of LER and LSR. The provider edge router acts completely like LER, and the provider router acts completely like the LSR, right? So in provider edge, we push and pops the levels, and in provider router we switch the levels, we swap the levels, right? And whenever a path is created from one edge one from one edge to another edge through all the switch or swap routers, we call it level switch path, right? As you can see, the green arrow started from ILER to ELER and passing through all the LSR. So this green arrow path, we call it level switch path, right? LSP. So this is all very general primary terms you need to get acquainted with, and I guess if you understand the idea how it works, it will be very easy to cope up with the idea of segment routing, right? So we talk about the LSP, the level switch path, as I said, from ILER to ELER via all the LSR, right? So this LSP is made this LSP is made or this LSP is maintained by the packets, but the decision comes from different level distribution protocols like LDP, RSVPT, or MPBGP, right? So you need to keep one thing in mind, that all the levels are actually assigned from downstream to upstream as the packet comes from upstream to downstream, right? So you need to think that whenever the packet is coming from upstream to downstream, the last router needs to know what to get, what to do with the packet, and what will be the level, and based on that, needs to decide what to do with the packet, right? So this is why the downstream starts the leveling, and when the complete leveling information is given or is made in all the routers of an LSP, the packet starts flowing, right? So whenever we're talking about the information of levels in all the routers, we are actually uh, talking about ILM, right? So as we move forward, you can see that this is the architecture we're actually talking about, or we using as an example. So here you can see CE1, customized router 1, and customized router 2. These two routers actually trying to talk through our MPLS network. The network is consists of two edge routers and six switch routers, right? Two LER and six LSR. So the PE2 or provider edge 2 router is actually talking to PE1, And suppose we are actually providing our VPN service via this network, and we whenever we try to insert the service into a network, as I said in the beginning of my discussion, that whenever the service is introduced into your MPLS domain, it is classified into an FEC. So we assume that the FEC for this particular service is VPNX, right? And we assume that the PE2, this edge router has decided to put a level of 1, 2, 3, 4. Now you need to keep it in your mind that this level 1, 2, 3, 4, it's only assigned for the FEC VPNX, right? So this is actually the service level of this particular service, right? So PE2 needs PE1 let uh, to know that whenever the VPNX, whenever any packet for FEC VPNX is coming to its network, it needs to maintain the level of 1, 2, 3, 4. So how does it do that? So that is where the BGP MPLS comes into picture. So PE2 announced that level to PE1 via BGP MPLS, right? So now if you look at this picture, CE2 and CE1 are connected trying to communicate over VPNX. So PE2 has already announced a level for this service, which is actually from the FEC VPNX, and PE2 has let PE1 know that, hey, whenever any packet for FEC VPNX comes to you, you need to maintain the level of 1, 2, 3, 4 for service, right? So now the higher level service informations are synced in P1 and PE2. But how to get from PE1 to PE2, that needs to be decided right now, because other than that the packet cannot traverse, right? Because it needs to cross all the LSR in its LSP, right? In its link in its level switch path. So by swapping levels, all the LSRs will take the packet forward by swapping the levels, right? So now we will see how it is done, right? If you look into the picture, the as I said, the levels are actually decided, or levels are actually assigned from start assigning from the downstream routers. So everything will start from PE2 for the assignment of level of transmission of this packet, right? Okay, is the level same for a packet from between PEs when pushing and stopping and popping? Yeah, that is what we're going to explain now, right? So the levels will be different, and the number of levels will not change, because only swap operation is going to happen in between the path. So that is what we're going to explain right now.
Did you want me to show my slide deck, Zobir, so that way the animation
that
work
Yeah,
better?
that would
Yeah.
be better, Warren. Yeah, I'm stopping my share.
I'll just move up because I just realized that.
Yeah, I have the PDF version only with me.
What slide number were you up to? Or PDF 16?
Yeah, 16.
So if you have a look at this, we've got our customers that want to create a VPN. And so we're going to basically have information sent from our perimeter edge, our provider edge, and it's going to send the information to the next adjacency. And so it's going to say, hey, I'm PE2, here's my label. What's going to happen is P3 is going to say, okay, so I know how to get to you is label 100. So that's how I can get to you. If I've chosen the right color pen, red, that's better. So I've gotten the 100. So that comes in to my table and I build up this 100. So I now need to give it a locally significant label to tell someone else about it. So I allocate a number 200 to that. So this is what PE3 has allocated to it. Then it advertises that to its adjacency and go, hey, if you need to get to this router here, give it a label of 200. Now that I've got that label and I've sent that out, P2 gets that information and goes, okay, anything for this PE2, I'm going to give it an out label of 200. I'm also going to send the interface. Now notice that we've got these interfaces here, which I haven't mentioned already. But what this is saying, if I'm going to send anything to PE2, it's going to have a label of 200 and it's going to go to this interface. This one here is going to know how to send it that way. Then router 2 is going to say, okay, I need to give that a label. So I'm going to say, let's give it a label of 300. And we're going to tell our adjacency about that. So I now tell router 1 or P1. P1 receives this information about P2. Now, these labels are unique to this individual router. So they could be not sequential like that, but we'll see it in our examples. From here, it then creates its own build-up, just like what we've done with the other. So we have our 300 coming in. We know the interface to get to that is out this way. And we then create a label to then tell our adjacency. In this case, is 400. Now notice that we're sending it out to another adjacency because at the moment there was only one adjacency here, but there's actually 1, 2 adjacency. And notice we send out exactly the same label to router 5. So that router 5 or P5 is going to do the same thing. It's going to create a table that knows what to do with anything with a label of 300 to send it out this interface here. Then it creates its own unique label and it's going to tell its adjacencies. So P1 tells PE1 to get to PE2, use this label, and we'll see the build up shortly, where it creates this label to get to PE2. The out label is 400, which means this interface here. But you'll also notice that, we haven't built that up, but normally you'll have this information going out that way. So you can have that built up there. So from here, it now has a label stack that it can send information. So anything that's going to be addressed to our customer on the other side of our network, we now have this traffic forwarding. So we've built up our label environment. We're going to now forward that. So the CE1 is trying to send a packet over to this side of the network. So it sends it to the provider edge. The provider edge goes and looks up, okay, I've got a packet destined for PE2. What do I do with that? It's going to start building this label stack. So it goes, okay, I've got my payload. So I've got my VPN label of 1234. But to get to my VPN over this side, I got to go to PE2. So I need to put a label of 400. So remember, this is the label to get to PE2.
Just a quick questions, guys. So can you tell that how does CE1 know that this payload of from CE1 needs to be assigned level of 1, 2, 3, 4? Can anyone answer that in the chat, maybe? So I'm going to explain again. So the payload is coming from CE1 to PE1, right? And P1 is exactly MPBGP. PE1 is doing the push operation, and it has assigned two levels, which we actually call the level stacking in MPLS, right? The first one is for service, and the second one is for transport. The service level is 1, 2, 3, 4. So how does P1 know that it needs to put the level of 1, 2, 3, 4 for this service? Via MPBGP, which actually told by PE2 to PE1. Yeah, exactly. Just to, yeah, there, this is the slide. So P1 told P2 told P1 over BGP MPLS that for any packet which is coming from FEC, which is termed as VPNX, you need to use the service level of 1, 2, 3, 4. So this concept is very important for you to understand that this is the service level, because if you get confused with service level to transport level, then things will be a bit difficult, right? Yeah, exactly. So as you can see, the packet forwarding mechanism, what Warren started to explain, the payload is coming from CE1 to PE1, and it does the push operation. There are two levels. We call them level stacking. The first one is service level 1, 2, 3, 4. The second one is transmit level 400. So where does this 400 came from? This 400 level came from the ILM, which was built just a bit earlier, and which was actually told by P1 to PE1, right? So so now as you move forward, as the packet moves forward, all the LSR, all the P routers, all the provider routers, they put the levels based on the ILM, which was just built a while ago, right? So you can cross match it. You can go back to your ILM slide, just one slide before, and you can verify, right? So here you can take a look that P1 is telling P1 that the in level will be 400, the out level will be 300. So you will see that P1 will assign 400, P1 will assign 300, P2 will assign 200, P3 will assign 100, and PE2 will actually remove the transmission level and do the push up pop operation, right? As Warren, you can move forward with the packet flow. Yeah, yeah, yeah. So the operation P1 push 1, 2, 3, 4, then 400, the operation of P1 swap 400 for 300, the operation of P2 swap 300 for 200, and the operation for P3, it will swap 200 with 100, and whenever the packet comes into P2, the pop operation happens and it removes 100 and 1, 2, 3, 4, both the labels, and based on the level value of 1, 2, 3, 4, it decides that this payload needs to be handed over to CE2, which is actually a member of the service FEC of VPNX, right? So this is how the packet reaches from P1 to P2. So if you try to get the idea straight in your mind, what happens? You connect the payload, you try to connect the service, your provider edge routers assign or classify the service into an FEC, puts the service level, and then your downstream edge router announces the service level to your upstream router via MPBGP, right? BGP MPLS, and then all the P router and P router, or we can say LER and LSR, they work together, build a level map, and those maps are set into all the routers. Now the path is ready to carry forward the packet. the packet comes into the upstream router, and the upstream router start pushing the level on the packet as the packet moves based on the ILM. As the packet moves forward, all these switch routers, they swap all the levels based on the previously built level map, and it reaches the egress edge router. The egress edge router does the pop operation and deliver the packet, right? So this is pretty much simple. This is what happens actually. So, Warren, I think I can move back to my screen again.
Okay, but did you want
Yeah.
to do the penultimate hop?
Uh, okay. Okay.
I suppose
Let's do it. Okay.
we don't need to do the layer. We can just show it in one if you want to move
Yeah.
back.
That can work as well. So you can stop your sharing. I can go back to my. Yeah. You guys are getting my screen.
Yep,
Cool. Okay.
but it's not full. Oh, now it is. Yep.
Yeah. So as we discussed, the push operation is being done by the ingress edge router, and the pop operation is being done by the egress edge router, right? Now imagine you have millions of VPN circuits, right? Each and every circuit, all the pop operation on all the circuits are taking place in only one single edge, egress edge router, right? So this is a big burden for your edge router. So in scenarios like this, what you can do, you can use the concept of penultimate hop pop, right? So you just do the pop operation just one hop before the edge router, right? So if you do that, what can happen that your provider edge router can get relief of one level of popping operation, and your loads can be shared among the routers, and this is how you can scale, right? So here, if you want to see the difference with the previous slide, if you see the previous one, where all the pop-up operation is taking place in the provider edge router, all the level assignment was started from PE2, right? This is the normal scenario with the level map, right? But when you are doing it with PHP or penultimate hop popping, your level assignment will start for transport will start from the node which is just intermediate node of your edge router, right? Here the incoming level will be assigned by P3 in this picture, and rest of the operations are exactly same, right? So whenever the packet comes to P3, it look into the interface, it pops the transmission level, and it sends the VPN level only to PE2. So your PE2 will get the packet with the service level, which is 1234, and it pushes that 1234 level and serves the packet to CE2. So this is the basic difference. If you look at the traffic forwarding pattern with the help of PHP, as I said, payload comes into P1. Everything what we did before is exactly same. The one and only difference which is gonna be visible is between the operation of P3 and P2. Earlier, P3 used to send the packet with two levels. Now P3 will send the packet to P2 with only one level, which is service level, right? So P2 is now popping only one level instead of two. If you go to the previous traffic forwarding mechanism, look at the operation of P2. P2 here, P2 is popping two levels, 100 and 1234. With the help of PHP, P2 now is 50% offloaded, right? For this circuit. So imagine if you have millions of sockets, your P2 will become a very will become 50% efficient, or 50% less loaded. So it will help you with a great deal of resource management, right? So this is what all PHP is all about. So one thing, if you look at this topology, you can see that all the links are actually carrying the metric of 10, except one, which is between P5 and P6. We have mentioned the metric of this link is 100. So if you want to try to calculate the path based on the IGP, you will see that the best path based on the IGP decision should be from P2 to P3 to P2 to P1 to P1, right? This should be the best path based on the decisions of your IGP, right? So that is what I wanted to focus, that the LGP forwardings always follow the IGP shortest path. So whatever the path you are getting from your IGP's decision, that path is going to be followed by LDP protocol. So it just uses the levels to carry forward the packet, but the path will be defined by your IGP, right? So as I said, the packet will move forward with ILM on each and every router, right? So all the routers should have its own ILM, and based on that ILM, the level operations will go on, right? And as I said, single LDP level is required to transport packet. In our example, our transport level to transport our packet, the level was 400, 300, 200, and 100, right? In our example, so these levels were used to transport the packet, and levels are assigned, as I said, from the by the downstream routers, and LDP level changes at each hop, because if you look at the ILM of each hop, they are different, right? So they are generating one level locally, and they are receiving another level from each intermediate router. So it changes, it swaps based on the level which it generates locally, right? So this is what we're talking about, LDP level changes at each hop as levels are locally significant. So this is a very vital and crucial concept you need to keep in your mind, that whenever we are talking about the levels in MPLS, they are actually locally significant. There is no concept of globally significant levels in MPLS, right? So this concept will come into picture when Warren is going to discuss about segment routing, right? So our next protocol is RSVPTE, the resource reservation protocol, traffic engineering. So what is the purpose of this one? Because we just saw that LDP is doing perfectly fine. It is taking the packet. It is helping the network to build a level map, and forwarding the packet based on the decision of an IGP. So what does this RSVPT do? So this RSVPT do traffic engineering, basically. As you can see in the diagram, the diagram is exactly the same, and all the links are having a metric of 10, except the one between P5 and P6, which has a metric of 100, right? So if you try to select the path based on the IGP, the path should have been from provider H1 to provider 1, then provider 2, then provider 3, then provider H2. But instead here we are showing that the path will be provider H1 to provider 1, then provider 2, then provider 5, then provider 6, then provider H2. And here, as you can see, the path is actually not taking into account which was decided by your IGP. That is what RSVP do. It does traffic engineering. it can create path which is not actually decided by the IGP, right? It can build in its own path. So that is how you maintain your own traffic path, your own customized traffic path, whether or not your IGP is supporting it or not. So that is actually everything basic concept of RSVPTE. So it's a big hectic the process. So you need to the concept of its working principle is you need to send a message. You need to send messages back and forth to create the path. So you need to work it out with the help of two kind of messages. The first one is actually called path message, as you can see here, from PE1 to PE2. So the path message is being carried forward based on my required customized path. And from P2, the response of this message is called the reservation message. So P2 sends back to PE1 following your own customized path, and this message is called reservation message. And when this message is forward, the local level is forward with this message as well. And based on this message, all the routers start building their own level map, and then the packet forwards based on the level map which was made uh, by the routers. So the if we try to sequence the working principle, the first working principle is to send the path message, and the second one is to get reply with a reservation message and with the local level information. And third operation is to build the ILM, and then the fourth operation is to forward the packet based on the ILM which is built by all the routers, right? So these are the four steps. It's pretty much straightforward. But the problem is that if you're working with RSVPTE, there is no unique local level as well. So as you can recall, just in the beginning of this presentation, whenever Warren Vai was discussing about segment routing introduction, there was what, there was how, and there was why. In the why section, there was a statement that the you need to keep state of your network, right? That is where segment routing comes in very handy. So whenever you are running a MPLS network and you are running RSVPT, you need to assign a local level per circuit, what should I say? Per tunnel. So whenever you are trying to assign another service like that with RSVPT, you will have to assign another local address for PE2, right? Here you can see that PE2 is having a local level of 999. And suppose you are trying to configure another service for another customer, so you need to assign another level for PE2. Whereas in LDP, one single local level would have done all the work, right? So the state increases. All the LSR needs to keep aware of the state of all the circuits who are using RSVPT, right? So so if you look at the working principle of RSVPT, it's a bit hectic and it's a bit bulky. Yes, you're getting the advantage of choosing your own path over your IGP, but you are going to sacrifice a lots of resources there, right? Exactly. So RSVP allows the construction of arbitrary paths based, as I said, it can create its own path, ignoring the path of the IGP. And it needs to be signaling in both directions, as I said, path message and reservation message. And it needs to maintain the soft state, as I said, which needs to be refreshed periodically. So your resources are going to be very busy all the time to refresh all the states of all the circuits who are using RSVPTE. And RSVPTE level changes at each hop as levels are locally significant, right? So same thing, the levels are locally significant. On top of it, for RSVPTE, for each and every circuit, you need to assign another new local level, right? So that is what RSVPTE is all about. So if we look at the challenges using RSVPT in LDP, you can see that RSVPT have the traffic engineering capacity, but it is gonna cost you something else. It needs to use too much of state information with refresh with a refresh of the state periodically, and also it creates congestion at your network core, right? And if you look at the LDP, it doesn't have the capability of doing traffic engineering. It relies completely based on the path of IGP, right? So imagine you get a protocol which have the ability of traffic engineering, and which have the what should I say, which can make your resources less hungry, right? So we need a mechanism that marries the best of RSVPT with the best of LDP, right? So that is where the segment routing comes into picture. So Warren Bhai, I would like to hand it over to you, but before that, I would like to ask our audiences if anyone has any questions. Hi,
There, there
can
is
you
one
run?
question in there in the chat.
Yeah, you definitely can, right? Warren Bhai, you
Yeah, the
can
question
adapt
is, can
to.
we run both the label distribution protocol and the RSVP on the same router? Yes,
Yes,
definitely.
exactly. So you can do it, but as I said, people actually doesn't feel comfortable to use RSVP because of the pressure of the resources. It's pretty much resource hungry, right?
Yes,
So
it's
exactly.
resource intensive.
Yeah. So
So
that's all about. Anyone has any kind of query so far, because you need to clear your understanding so far very clearly. Otherwise, when Warren Bhai moves into segment routing, you will get lost, right? So talk to us. Raise your hand or type your questions in chats or Q&A, whatever, if you have any. I don't see anything, Warren Bhai. So I think
I might take over the screen and just bring up the web page, because this might be a good time to stretch our legs and have a coffee to come back into the segment routing introduction. So we're at this point here where we're about 90 minutes in. We've covered quite a bit of theory so far, but we haven't really gotten to the segment routing. For those people who joined a bit late, I'll just throw this into the Zoom chat window, so that way you can grab a copy of it and catch up on what you may have missed in the slides. So we'll have a 15-minute break now. Get a glass of water, cup of coffee, stretch your legs, and come back and we'll look at the segment routing. So I'll just start a timer. Let's wait for that to start. So if there's no more questions, we'll start our break and come back shortly. So I hope everyone's been able to stretch the legs, get a drink of water, and ready for the next session. There is a lot of theory to cover for segment routing. I'm hoping I can spend a little bit of time just getting you started on the lab so you can get some hands-on to get familiar with the segment routing concepts. So thank you, Zabir, for your intro or recap of MPLS. Hopefully we can utilize that to build on what we've done. Is everyone ready? Can I get you to click on the reaction for the green tick, or actually, I don't know if you've got reactions in the webinar mode. Oh, it looks like you may not. So I'll get you to just type in yes if you're ready for me to start into the chat window. Oh, I've got one person that's ready. That's good to see. So when we look at the segment routing, it came about from this concept in this working group called source packet routing in networking. So the idea is that the source is going to decide how to route the packet through your network. And it's called Spring as an abbreviation. And it's still being created as we speak. The working group has got all these drafts out, and there was even a few updates this month to the Spring documentation. But the idea was basically figuring out how can the starting node specify the forwarding path, how my packet is going to travel from point A to point B. You think about your own network. There might be certain networks on the internet that you don't want to transit, or you don't want your packets to transit. Can you control that in some mechanism? Or you might want it to be in regards to your customers. When they're using your network, how are you going to control that? Or the customers might want to make sure they can control that. So the idea is building on that network virtualization and having this multi-topology network on the same physical infrastructure, but being able to have various interconnectivity divided out. And so you're going to build up with that using some sort of link association and have this fast reroute, but you have your network as a whole, you've got your links between your nodes, then you've got a path that goes from node A to node B, and being able to build in protection for that. And so all this standardization that they're trying to build is to make it easier for us engineers to have a reliable network. And there's all these topics here that they're trying to cover, and some of the day-to-day things that we're going to have to do. So the idea of this was to come up with some sort of concept where we didn't basically have to tear down all our networks and start again. So there can't be a flag day to basically build out your network from scratch. So it has to be incremental. It doesn't need to be done in one big chunk on your network. And it must allow you to put extra information or some sort of policy state into the packet header. And when you get read, when that information is read as it's sent through the network, it should be able to give some sort of idea of what to do with it. So to give you an example of some of the documentation, I'll get you to go back over to the wiki page, and I've got a link there to this RFC 7855, and that's going to be the problem statement for this source packet routing in networking. So it was actually a concept that's been around for nearly 7 years. So way back in, actually just over 7 years, but way back in 2014. And it became a draft in 2016. So this information is how they came up with these concepts and what the requirements were, if you want to go have a look at that. The other thing is that because it's an ongoing development, we're not going to be experts at this. We can give you guidelines and give you ideas on how to use it, but I would also recommend that you go to the latest documentation. And I've got a link here on the website that you can open up and go have a look at as well. And just to show you that it's ongoing, this updates and this working group is having lots of discussions. There was quite a few documents that were released this year, and one was released only a few days ago. That opens up for me. It's actually quite slow. So you can see here, February 2021, you've got some documentation there. You've got April, you've got March, April, and 8th of June. You've got this integration of network service header and segment routing for service function chaining. So there's all these concepts that are being discussed and updated and documented, and various network operators are having their input. So if you are a large enough provider and you want to influence the documentation, I highly recommend you join that. But in its core, what we're trying to do is basically get our source to give the path to the destination. So we're going to be basically embedding that path inside the packet. And it relies on two types of data planes. You've got the MPLS one, which is what we needed to recap so you could understand the MPLS. And then if you look at SRv6, which is segment routing v6, it uses IPv6 to put the heading, the information into the routing header. So what we have is that our source determines where the packet goes. And it uses some sort of instructions to do that. For example, it's going to use something maybe like send it to this node. Or it can just say send it via this adjacency. It depends on how you're going to set this up. And there's different methods of strict or loose. And I'll talk about that a bit later on. Now, what's going to happen is that the intermediate hops are going to inspect that list, and then they will decide how it routes based on the instructions, those labels as such. So for example, we've got this use case here where we've got our customer on the left wanting to communicate to its end device on the right. So we have this VPN that occurs. So information gets sent from our destination back to our source. And it builds up that label, which we've seen already. What's going to happen then is the perimeter edge is going to build up this addressing and figure out how to communicate there. That's how we'd normally do it. What we want to do, though, is to be able to start building out some more details for that. So some things that we can add to this when we use segment routing is this fast reroute. What happens when we build out this if something goes wrong? So we want to do things like look at the pre-computational path. So this means that we can now have an overview of our network and we can build up this backup path. So that way we can figure out how to get information sent across. What about fate sharing? Fate sharing is where you've got links that are using the same infrastructure. So for example, you've got multiple wavelengths on the same fiber. So you've got this shared risk. If that fiber goes down or it gets damaged, anything going across that is going to have a problem. So you need to think about the risk constraints for that. Then you have things like the micro loop avoidance. So this is basically creating a loop-free alternative path as a backup without having to go create this new calculation based on your IGP. So with segment routing, we would use it from a traffic engineering point of view. You're going to think about how are you going to build that out, depending on what use cases you have. So you've got things like being able to forward your traffic over paths other than your normal shortest path. And we saw that in the example with the MPLS, we had a segment that was 100 rather than the 10. And so if we wanted to force the traffic over that, it could be difficult. You've got other things that you need to be aware of in regards to being able to break apart what you normally want to do with networking. The difference between loose and strict is that loose allows me to just say, hey, send it to this node and make sure you go through at least this node. With strict, I give a list by list of the hops I want the device to go to. So I basically build out more details for that. I'll come back to those use cases after we break it down into some examples for you. So from an architecture point of view, we're basically using our node to steer where the packet goes based on a list of instructions. And those instructions are called segments. A segment can represent something from a topological point of view or from a service. So it allows us to steer where the flows are going without having to know all the intermediate points. So we can say, send it out to that node. Now, a segment is basically just instructions for the node to execute. Now, those instructions could be things like using the shortest path, or send it out this interface, or deliver it to a service. We also have a global segment. Global segment is shared between all of the segment routing capable routers on your network. So that means that they all have the same label, means the same thing for all of those routers. So you've got your segment, which is the instructions. You've got a global segment, which allows you to have those instructions shared across all your network. And then you have things like a local segment, which is related to that one device. Now, with MPLS, we have this label concept. With segment routing, you have this segment identifier. So that basically is going to identify that list of instructions or that segment that you want. And that's going to have an index value similar to your label that you get for MPLS. You could also specify as an absolute number. When we create a list of instructions, we've got that segment list. And that's basically taking these identifiers that we've talked about here and putting those into an order so you know which way the labels should be going. And then from that, you have this domain. So all of the routers that are participating in the one routing model are part of that segment routing domain. Now, this is all terminology. It'll make more sense once we start building things out. I tend to like doing the practical first. Makes more sense from there. So we've got our segment identifier, we've got our segment, we've got our global segment. What we have is a block, and these are going to be the labels that you are going to assign. So you've got these segment routing global block. So in our MPLS theory, we had some examples where the router, the PE2, gave a label of 100 for P3 to then know how to get to the customer. Similar concept with segment routing, we have this label there, but this label is available and all the routers see that. So when we have our segment list, it's basically a list of those segment IDs. Those segment IDs allow you to then figure out where to send the information next. And you have it what's called an active segment, and that must be received packets with a label at the top, and the MPLS will decide what to do with that. Whether it's MPLS or SRv6, it will look at that header information and decide what to do next. Now, that segment router is basically a list of the nodes or ingresses that you want to do. Now, to break it down, if we go to this area here, from a terminology point of view, you've got your IGP segments. The IGP segments are going to basically have two families. It's going to have information about your prefixes, and you'll have your segment ID in there. You also have information about your adjacencies. So you're going to basically have information come in, and you're going to make a decision on whether you send it to a node or to an adjacency. Based on that is the information that you're able to set. If I'm going to set it to a node, that node could be any cast, it could be just a node, or it could be some sort of binding segment that I've set up. So being able to map to a server or something like that. So terminology from a node point of view, that's going to be anything that is capable of understanding segment routing. The segment ID is going to be globally significant. And when I specified the node SID, that's basically giving instructions on where the packet should go to next, how to forward it. And it's going to use the shortest IGP path. Obviously, it needs to know how to get to that. So it's going to use some sort of routing protocol to get there. And I'm going to have to manually configure that. Anycast is, does everyone know what anycast is? Being able to just send to the closest addressing. So an anycast prefix is going to have a SID similar to the node SID. It's going to be globally significant. So all of the devices will see that and know how to get there. Again, you need to have this connectivity using some sort of IGP, in this case, the link state. The next one is the adjacency SID. And this is just saying, how are those adjacencies set up? And what I'm doing is saying, if I send it to an adjacency SID, it must go to that node that is adjacent and so on. Makes more sense once we start building out the use cases. So the same concepts of what we had for the node, the anycast, and the adjacency are very much the same. It basically is a way of identifying the area. So if we bring up a whiteboard, and we've got our routers, I think I've put too many lines in, but anyway. So we've got our node SIDs would be looking at this as our node. So if I wanted to send information to P1, I would have a value for P1 as a node SID. That might be 16,001. And it wouldn't matter where I am in this network, this 16,001 would mean the same. So if this device here, P6, saw 16,001 as the label, it will know that it needs to send it to P1. If I didn't give any other instructions, it would use the shortest path based on the routing protocol. What I could do, though, is use an adjacency SID. So that's saying this link between these two devices or this link between these two devices are given a, so let's go adjacency. Let's say this one here is given 17,001. So again, doesn't matter where I see it in my network, it will know I need to send it to this adjacency location. So if I was here, I would then need to think about the shortest path to get to that location. And it would aim it there. Anycast is being able to have multiple devices with that one SID, and whichever is closest is going to get the traffic sent to it. On top of that, we've got our border gateway protocol, the egress peer engineering, which is enabling us to add some extra information there. So that way we can now direct our traffic via uneven cost exit points or different locations. And I've got a nice use case a bit further on that will help explain that. But the idea is that you're going to be able to specify the same sort of concept of a peer node, and then you've got local significance once it reaches there. So it will be sent to this exit point, so your provider edge, and then the provider edge will look at that local SID and decide which node it needs to send it if there's multiple connections out of your network. The same for this peer adjacency segment. It will come to that provider edge, and then from the provider edge, say if we had, say here's our network here where we've got 4 core, and then I've got a network over here, and I've got a connection there, and then I've got another network here, and I've got a connection like that. I can start deciding on where I'm going to send that. So I have the global SID that gets it delivered to this exit point. And then from that exit point, I can determine where I need to send it. See how this has 2 links there? I can say, doesn't matter which one you use, just use an adjacency one of that. Or I can specify a specific node, or I can use a peer set, which is saying these 2 lines here are seen as a peer. Whichever's free, just send it out that way. So when we are looking at our segment operations, very similar to MPLS, where we're going to be looking at the label or the segment ID and deciding what to do with that. So from a segment routing terminology, push is very similar to the MPLS. Push is basically inserting some sort of segment at the top of that list, some sort of ID. MPLS is obviously pushing a label at the top of the label stack. IPv6, if we're looking at SRv6, is setting that first segment in the IPv6 addressing. Next is basically saying move to the next active segment in that list. And it's popping if you're looking at MPLS, and then the activation of the next IPv6 header that you have. And then continue in the segment operations is meaning go and do something else. In MPLS, it's swapping that top label. So from the MPLS data plane point of view, we're not going to focus on SRv6. We're mainly looking at the labeling that will happen when you do segment routing. So what you're going to have is this label added as a segment, and it creates this list for us. So what you start off with is this SR global block. So segment routing global block, and it usually starts around the 16,000 to 24,000 mark. It can go up higher, but in most cases, it comes back to what your provider has set up, your vendor equipment. So you're going to create a set of local labels that are reserved for this global block. Then you're going to share that with all your devices. So when you start setting it up, and you need to come up with what you're going to label. So you might start off with just labeling your nodes. Simple process. So you're going to allocate a value to your nodes. You might do it as an absolute value. That then means that they will become identifiable in the segment routing global block once it gets advertised. So to give you an example of this, we've got these 3 routers, and we're going to set them up with exactly the same segment routing global block. So I've said, okay, you're going to be allocated 100 to 199 for the whole 3. So that means that they've reserved that block of labels. I've then said that router 1 is going to have the segment ID of 101. Router 2 is going to have 102, router 3, 103. What's going to happen is that each one of those are going to then advertise that to each other, what they know about the network. So what will happen is that the edge routers will learn about the other routers' values. So in this example, we've got router 3 is now going to know that my in label is going to be 103. Anything else going outside is going to be removed, and it's a local interface. So that means 103 means myself. For router 2, 103 means exactly the same as 103 for router 3, but I now have a different interface. I'm sending it out this interface here. I also, depending on how it comes in, so if I have the in label, I know how to send it out that way. But if it's using penultimate hop, remembering that we want to use it for scaling, I would not have an out label at this point, but I still have that same interface there. That then gets shared with router 1. Router 1 now has the same label as the other 2 routers, and it gives it the same label going in as well as going out, and it associates it with a interface. So this is a little bit different to when we looked at the MPLS. With the MPLS, we got told what label to use, and we created our own locally significant label to then tell our adjacency. So building up on this, what we have now for router 2, it does the same process. It's going to tell its adjacencies here's my information, here is my label. And so router 3 builds up its ILM, label mapping. It also can build it up with penultimate hop popping. And the same for router 1 with doing the penultimate hop popping. So they've now got router 1, router 2 should have labels for 102 and 103. Then router 1 does the same process and tells the world about itself. And the other 2 routers build that up. And in the end, each one of these routers are going to have the SIDs of 101, 102, and 103 in their ILM. And they should know how to send it based on that. Now, what you could also do is figure out where you're going to put this global block. You might want to specify it to be different on each of these, because if I do that, I may be able to follow the path a little bit easier if I want to troubleshoot. So I can have these different values in there. So I can allocate an index offset. So that way router 1 will have the first 100, router 2 will have the next 100 in the global block, router 3 will have the next 100. So as an example here, I can specify this index value and allocate it there. So to just show you that from a graphical point of view, so we have P3 is going to start advertising. Oh, sorry, I should point out here. We've got our segment routing global block are different on each of these. So 100 to 199, 200 to 299, 300 to 399, and I've got an index now. 1, 2, and 3. So what does that mean? So when router 3 goes to tell the world about itself, it's going to give out its label as starting at 300, but with a 3 added to it. And it's going to tell the world about itself, and the other routers will build up their ILM and be able to then figure out what to do with it. But if you have a look here, what has changed compared to the global segment routing block that we had before? We still have that global segment routing block, but now we've got a different section of it. So I've received the information from router 3. So I know it as 303, but do I have that block in this list? No, I don't. So I need to give it a label from my allocated numbers. Then I tell router 1 about that, and it does the same. It looks at that out label and it comes up with its own in label. Router 2 is going to do the same. It's going to go out and tell the world about its labels. Router 3 will assign its own in label for it and out label. And router 1 will do the same. Router 1 goes off and does the same. It's going to share its label. Router 2 allocates its own label to that, and then so on and so on. Any questions about that? So what we might actually do, it looks like there's something in the chat.
Yeah, Warren. So there is a question in the chat.
Okay, so what's the difference between PHP and no PHP? So when we look at that, this is not a very good example because there's only 2 hops. The idea is if I had multiple devices and we're all connecting to this and we had our customer here. And we wanted to send traffic to these devices on the customer's network. And I might have, at this point, there's only 3 of them. If I send everything with the label on it still, going to this router here, this router now needs to do the removing of all those labels before it sends it to the customer. So from a scaling point of view, the more labels that this router has to remove, the more work it has to do. So with penultimate hop popping, what you're doing is that you're letting the one hop back know that because router 3 is locally connected or knows how to route to this information to the customer, it doesn't need the label to know how to do that. It has that physical connectivity. Whereas these devices are not connected directly to the customer, so they still need some sort of way of routing their packets destined to the customer. So it uses the label, but instead of sending it with the label onto the exit point, they remove the label because they know how to get to the exit point, but they don't know how to get to the customer. And so that's what the penultimate hop popping means. So when we look at that, I'll just remove the, that's on this side. So when we look at that, you'll see here that when I don't have the penultimate hop popping, I actually have this label attached to it. So what I'm saying is that my out label is going to be 101, my in label is 201. And so I'm actually keeping the labels on there, I'm swapping. Whereas if I use penultimate hop, because I'm directly connected to here, I don't need to add a label to it. I know which interface to send it, but I will be telling router 3 to get to router 1, use 201. And we can see that it's using 201 here to be able to send to P2 to get to 101. The issue is if all of the exit nodes had to then take those labels off, they're going to have extra workload from that point of view. Does that answer your question? So what I'm going to get everyone to do is to go over to the web page and log into the Academy virtual lab. So I'll just copy that. And I'll paste that into the Zoom chat window. Because it'll make a little bit more sense when we start looking at the network topology and we build out a very basic example of this. Otherwise, I'm going to rattle on with all this theory and you may not understand it in the end. So once you get to this link, it will show you this segment routing virtual lab using the Cisco IOS. You can either click on register now or log in. I'm going to just take it off screen while I log in. Now, if we don't finish the lab, that's fine. You can complete it in your own time. There's plenty of time. Once you've started the virtual lab, you've got 7 days to finish the activity, and you can always pause it and come back to it. So I'm logged in now, and you should get this option to launch the lab. I click on Launch Lab. That's going to now go off and start building the virtual environment for you and present it to you in a web page. Now, I'm going to use a quick option with the lab environment. It has the option to type the text for me into the router interface. The reason for that, we've only got about an hour or so, hour and a half left. And so if I started typing, it's going to take forever. But I'll just let that start up in the background. So while that's starting up, what we're going to have access to are 6 routers, and we're going to start building out our environment for that. So I'm just going to scroll down until I get to the topology. I'll open that up. So this is the basic topology that we're going to have. In here, we've got the 6 machines, and I'll just create my annotation. Just a bit slow. So we've got our loopback addresses in the 10.0.0 range, /32. So you can see 10.00.1 is for router 1, .2 is for router 2, .3 is for router 3, .4 is for router 4, .5, and .6. So that's how we're going to start communicating from there. We've also got the point-to-point networks using the /30, so 10.1 for our other IP addresses. Remembering that segment routing still relies on the connectivity of your network. So you still need to have that underlying routing protocol to be able to know how to get around your network for that. So we're going to create this topology. Should already be mainly set up for you. Then we're going to build out our sRGB, our segment routing global blocks, and we're all going to start with the same global block, and we'll see how the labels are going to be propagated through that network. So let's clear that. Yeah, that's nearly started. So to get into the devices, you've got your username and password under this resources tab if you haven't used the Academy Virtual Lab before. So you've got resources, you've got the username and password there. There's also another password called for lab configs. Under the instructions, it's going to give you an overview of the addressing. It's going to tell you about the OSPF configuration that is there. And you can go have a look at that configuration on that first page if you want. But there's a rough idea of that. I'm not spending time talking about the underlying protocol and routing information. I'm assuming you've got some of that knowledge. So we click on Next. And what we're going to do for the first step is set up our basic segment routing. And we're going to give every router the same global block. Once we've got all that global information set up, we're then going to start checking our connectivity for that. To get access to some of the routers, you can just click into the window and press enter, and it should prompt you for the username. In this case, it's APNIC, and the password is training. And then if I want to go into enable mode, I go enable, it's lab config or lowercase. You also have this lightning bolt in the top left-hand corner. So if you wanted to type out the commands, or experiment with other commands, you can paste them via this clipboard option if you want. So the first part that we're going to do is that we're going to build out our SID, our segment IDs for our routers. Starting at 16,000, we're giving an absolute value of 16,001 for router 1, 16,002 for router 2, all the way down to 16,006 for router 6. And we're giving our global block of 16,000 through to 23,999. So ideally, at the end of this first part of the lab, you're going to have this information set up. So you've got your OSPF area 0, you've got your segment ID for your different routers, being 16,001 through to 16,006. You're going to have your segment block for your SR global block of 16,000 through to the nearly 24,000. Is everyone clear on what we're trying to do to start off with? So to build that, we're going to have to set up our address family and set up our details there. So here's the password if you didn't understand what I said before. So it's password lab config. We're going to enable our traffic engineering tunnels. So we go into our configuration, conft, and anywhere where there's a T symbol next to the text, you can click on that and that will directly type it into the active window on the left. Now, if you're new to this, I recommend that you type it out rather than just clicking on the T, because you're not going to learn anything from doing that. So it takes me into the traffic engineering tunnel, and I'm going to specify that I want to configure segment routing for MPLS mode rather than IPv6. Looks like there's something in the chat. So we add the segment routing, type that in, and then we've got to assign our global block. And this is what we're going to type in for the 6 routers, exactly the same. Nothing changes at this point. So you can type this into Notepad and then copy and paste it into each of your routers. So if I do a show run on that, now the problem will be I can't send. There we have it, just at the top there. I can't go back, unfortunately, can't scroll back. But we've got our segment routing, MPLS, global block, 16,000, and then 23,999 is in there. So we know that we've got that first part created. Now we need to go into a sub mode to start specifying our address family for our loopback address. So that's where we go into our prefix SID map, and then we create the address family. And it helps if that's going to have an error. So I'm just going to jump out of that and throw that back in. Go into our address family. And this is the only line that's probably going to be different. And that's going to be your loopback address and the label that you're giving that loopback address. So you would change that in your Notepad or your configurator IDE and make sure that's updated. So from there, we're ready. Now we need to tell our OSPF to advertise that. So we go into our router OSPF configuration and we specify that we're going to configure segment routing. So that way OSPF is going to tell the world about our labels that we've got up here. And we're saying which area are we going to connect to. So in this case, it's area 0. And we're saying The router ID, in this case, is our loopback address. And we're enabling the traffic engineering for our area 0. And from there, we have this operations and maintenance. So we specify that, and then we can save it. But in theory, that's now going to be telling the world about that. To build out this, we need to do it on the other 5 routers. So again, this is why I'm not going in and typing it, but all of the commands are there. So if you want to copy those into Notepad and see it as one big list, you can. Or if you scroll down, here it is here. So essentially what we've done is that we've specified where we're going to label our environment. So I'm just going to go back into annotate again. So this part here is talking about creating our segment routing block and our segment ID. This one here is basically telling the world about that information that we created up here. So it's basically advertising it to the rest of the network. So you configure your global block and your SID, and then you tell the world about it here. That's all you're doing. Now, out of all of the configuration, the things that will change between the routers will be the absolute value of the SID, the loopback address, and the router ID. Everything else will be the same over the 6 routers. So I won't go ahead just yet. Once you've logged into the Academy and you've configured router 1, can I get you to type in yes into the window so don't leave anyone behind? So type yes into the chat. If you've got any questions at this point, type that into the chat as well, or the Q&A. Router 1's done, excellent. So if you have a look at the lab guide here, you've got this hyperlink. So select router 2. So all you do is you just click on that, and that will dynamically change you to router 2. Or you can go to resources and just click on router 2 from the resources. So we've got the router 2. Let's press enter a couple of times. Username is APNIC. Training. Enable lab config or lowercase. And from here, most of the labels, most of the next configurations for router 2, 3 through to router 6 are in a block like that. So as long as you're into the config mode, it should go out and build it for you. But again, if you've got the time, I would suggest going back over this and typing it out and learning the commands in more detail. So I'm just going to step through and do that for the other routers. Remembering really the only thing that's changing at this point is the label, the SID, and the loopback details. Router 4. Router 5. And then finally router 6. So once everyone's gotten to router 6, can I get you to type in yes into the chat window, or that you let me know that you're done, so I can then move on to the next part. The next part is we're just going to start looking at our segment routing information and how it's been propagated through OSPF. I don't want to leave anyone behind. This is where we need to play some music, Zabir, while everyone's doing their lab.
Yeah, not a bad idea actually.
I don't know if I shared my screen with music enabled.
Yeah, the participants also agree.
I'm not a very music orientated person. I should, but I'll see what I've got.
I'm missing Rene here, or Mark Tinka.
Oh yeah, Mark Tinker. Yeah.
Yeah.
I'll just stop my share and see whether. Oh yeah, I can share sound. But will we be breaching anything? What sort of music do we want?
Maybe some soothing, something soothing.
Stress relief. It might be too stressful.
Makes perfect sense.
Let me know if it gets too noisy. So how's everyone going? Can you type in the chat window? Done. Excellent. That's the time for you. So what we've got here is our configuration. Now that we've got that, and I've waited a little while, in theory, everything should have been propagated through our OSPF. So hopefully we're going to get an overview of some of the labels that are there. So if we want to have a look at our MPLS labels, we'd have a look using the show command. So if we go back to our router 1, and I didn't do it end all right.
Warren Bhai, your screen is not there.
No, it's not, is it? It's gone to a different side.
Yep.
Thank you for letting me know. That's better. I'm just logging back into router. Does the screen come back? You there?
Yes, yes, yes.
So just using the show MPLS label range is going to go off and show us what has been assigned to this router. So we can see here that we've got the minimum and maximum label range, and it's going to be for our SR, which is our segment routing. There's no checkpoints at this point from there. If we go down a bit further, we can then drill into that, into looking at our forwarding table. How are we going to get information around our network using MPLS? So go show MPLS forwarding table. If you just type in FOR and press tab, it's going to show you what information at any point. If you don't understand what command to put in next, you can do a question mark and it will give you more details about what is expected. So in this case, if we just leave the show MPLS forwarding table and press enter, we should hopefully get some brief overview of what's happening. And we can see our loopback addresses. Yes, so we've got our loopback addresses of the 00 network, so 10.0.0 are our loopback addresses. Our 10.1.0 are all our physical links, our point-to-point links. Easy way to remember it at that point. So if we have a look at our labels that we've got here, we've got information for getting to router 2, router 3, router 4, router 5, and router 6. And we can see information related to that. We also have information about what the prefix is for that label, and then what is the outgoing interface and the next hop for that. Can everyone see that? And just to make it a little bit easier, I'm just going to bring up another slide deck. Just want to jump out of this one. Just to clarify, so here's our environment that we're working on now, our first lab. So we've got our information set up for these. I'll just grab the pen. So we've set up our sRGB as part of our configuration. We've also set up our SID for each of our routers based on the loopback addresses. Now, the loopback addresses are going to be a little bit different in this one, but we can get the idea. So the commands that we went through are in here where we're talking about enabling the traffic engineering functionality. So again, you'll need to check your licensing for your devices, make sure that's the case. We're specifying our global information for our sRGB, enabling the routing for that and setting up our router ID. And then we're specifying how our traffic function is, or traffic engineering information is going to be shared with OSPF. So when we look at the show MPLS label range, it should show us what our minimum and maximum label range is. We can also drill in and do more detail on that label and look at the table detail specifically. So if we go back and have a look at that on our lab environment, now depending on the licensing, show MPLS label question mark. We've got our range, show label range. In this case, we don't actually have that on that option available. So we can do range and that's it. So in this case, we don't have all the functionality for those commands. So that's all we can do for that. And we can only do the label range there. I can't drill down into more detail, but what we can do though is have a look at that forwarding, and we've looked at that using this previous command for the forwarding table. Now in the forwarding table, it's going to give us important information about where to send and what's happening from an MPLS point of view. So if we have a look here, we've got our prefix SIDs, the information on how to get to those next locations. So it shows us our local label, what the outgoing label is, what the prefix ID is, the outgoing interface, and the next hop, if we're lucky. And we can see that in this here. I've got my, just grabbing another annotation so that can happen. Got my local label. I've got my outgoing label. I've got my prefix or tunnel. I've got my outgoing interface and my next hop. And we can go look at the network topology and to confirm that. So if router 1 wants to get to router 2, it's going to pop the label because it knows how to get directly connected to that. And it's going to send it out interface G1. And the next hop is that IP address. Let's double check. So I'm going to bring up my topology, see my network topology. If I bring that up, I can see I've got too much annotation there, so I'll just remove that. So router 1, it wants to get to router 2, which is a label of 1602, which we know about that. we know that if we want to get there, we want to send it out GI1, which is true. And the next hop is 10.1.0.2. And that should then get me to that router. So we want to make sure that we've got the configuration correct and just review what you've got set up, and what is shown in the MPLS forwarding table matches what you expect. The next item that we want to check is to have a look at the OSPF database and see what information it shows us there. So if we open that up, so we're looking at show IP OSPF database, opaque area, self-originate, and it's going to tell us details about what my router ID is, what my area is, and the router information. And if we drill down a bit further, it's going to tell me details about how my connectivity is and what my SID value. I haven't got a notation on, but I've got here the label of 16,000 for my segment routing range. And it's got my segment routing algorithm that's being used. And the advertising router in this case is myself, 10.0.0.1. So that's my first segment routing identifier. I scroll down a bit further. I've got my advertising router, a little bit more details. So in this case here, I've got a remote interface address, 10.1.0.2, and it tells me the link state and information about how to get to those connected devices. So the information that we want here in particular is the algorithm that we're using, segment routing, and then the label that is given for that segment. And then we've got our connectivity for our other locations. Now the IP addresses are a bit different. I should have updated this. So let's have a look at our forwarding table, our CEF. And that's the next command that we've got in this example here. Oh no. I don't think I've got it there. So let's try show IP CF 10.0.0.2/32. So looking at that, we've got information about how to get to our next hop in my routing information for that. Let's try 6. Let's see how we get to loopback 6. And in this case, we've got 2 next hops. So from router 1, I can go to router 2 and then go out to the next hop 1.0.6 and get there that way. But we can see that the local label matches for both of those. Any questions about that? Now, if we want to drill down and get more information about our forwarding table, we can do things like this. Drill down and get details about that. So let's have a look. So forwarding table. The more details that we can do a destination prefix. Then we can specify the interface if we want to look at that, or go into details for that. So let's have a look at the forwarding labels. 1606 is our label, 16,006. And let's do detail and see what information that gives us. So we know that there's two ways to get to router 6 from router 1. So the first one is showing us that the local label is 16,006. The outgoing label is 16,006. It's using that prefix, and we can send it out GI1, and the next hop is 10.1.0.2. And we've got another way of getting there using the 10.1.06 as our next hop. I should go have a look at our topology. Oh yeah, it is. I couldn't figure out why I was having 6, and that would be why. So yes, that's why it's got that label of 6. I can't annotate this, but that's because we've got 10.1.0.6 matching this one here. So we know that our next hop can go that way or the top path. Any questions about that? So we can see our connectivity. We can see that it's been advertised into our OSPF, and we can see our labels that have been associated with the different paths, as well as our loopback addresses. So from there, we can test that using pings and trace routes if we want to do that. So in the lab guide, it gets you to do it on all of the different routers and go through and have a look at the labels. Are there any questions about that? Just scrolling down until we get to the next activity, because that's what I want to do, is the traffic forwarding. So I'm still on router 1, as I can see in the name up the top here. So this is where we want to go and show the details, which I've just done. And we've looked at the routing information. Now we're going to use the ping command to go and see where our traffic goes to. So let's do a ping using the label 1606 output interface going through our gigabit Ethernet 1 and specifying the next hop as being router 2. So let's force it out a certain location, and we should see that we've got a response. In that response, we've got the information coming in. So code exclamation mark is a success. And we've got the escape sequence. Yep. So that's all fine from that point of view. So in this case here, it should be good. As long as you've got those exclamation marks, that's what we should be after. But it doesn't really tell us which way it went once it got to that setup. So if we think about our, oh, this is the next lab. That's not what I want to do. We think about the pathing that it takes. So this is where we do a trace route using the same sort of concept. We're saying, go to this label, 16,006, send it out our gigabit Ethernet 1, and let's see what happens with that. So when we send it out, we're going to get this information. So we're going from 10.1.0.1 to 10.1.0.2. Then it goes to 10.1.0.10, and it's got an explicit null or implicit null to remove the labels. And then it gets to our 42, and we can check that addressing. So we know that 1 and 2 is router 1 going to router 2, and then we've got 2 to 10. So let's check that. So if we have a look here, we've got the trace route went from router 1 to router 2, which was 1 to 2, so 10.1.0.2. And then from router 2, it went down this way to 10.1.0.10. And then from that, let's have a look. It's gone to 42. So here is our 42. So it's then gone up this way. So it's used the label and it's calculated the shortest path. But if you have a look, if they're all equal, this could have been the shortest path. So if we said they're all worth 10, you've got 10, 10, 10. So that's 30. If this was 10, 10, 10, that's 30. So you now have this option to do traffic engineering somewhere here. So that way you could specify a specific way of going. So we've got our ping being able to connect to our router 6. We've got our trace path that was able to show us which way that label was sent through the network. If we do the ping from router 1 using a different interface, what's going to happen? So we're going to do it now and sending it through the bottom layer, through this bottom link here, rather than through the top link. So let's do a trace route and see what happens then. Ping will work, but yep, we've got the response. Do a trace route. And what do we notice here? It's gone from my router 1 to my adjacent router, which is .6, then from .6 to 22, then to .38. So let's see where that takes us. So we have router 1, and I need to turn on annotation. Router 1 sends it to .6, .6 then sends it to .22, which takes it up this way. Then router 4 sends it to .38, which delivers it to router 6. So we can see that going in the opposite path to what we saw previously. In this one here, we went from here, up this way, down this way, and then up there. So for the next lab, what we want to do is to have different segment routing global blocks. Looks like there's a item in the chat. So in your example, so someone's put in the chat, in their lab, it goes through router 1, router 3, router 5, router 6. Why do you think that would be? So router 1, router 3, router 5, router 6. Again, if we look at our costing and they were all equal cost, it's still going to be the shortest path. So you've got 1, 2, So 1, 2, 3 hops to get to there. 1, 2, 3. So it's the same path. So it's going to come back to how your routing protocol has calculated that and which one was converged first. So if you had configured down this way and it had the convergence before the top, that could be why. That's one of the disadvantages of relying on dynamic routing protocols. You don't control that path that it calculates for the shortest. Obviously, you can modify metrics to control what path it will take, but if we had it all as default, it's the way that the algorithm decided. So in our next example, what we're going to do is we're going to specify a relative SID index and have different segment routing global blocks for each of those. Now, this relative segment index is basically saying the value that you want to start with. So what that means is that I'm going to tell the router 4 and the router 1 that my index value is 200. So in their local block, they will assign, in this case, I start at 16,000. So I add the 200 as the index value to give it a label of 16,200. For router 4, I've got a range in the 19,000, index value of 200. So that will give me a label for router 2 of that. So you do need to be aware of what your index values are that you do share between your routers so you don't have overlapping. So going back to the lab guide, if we scroll down, it's just getting you to do trace routes, verifying traffic routing. We can have a look at that. Doing ping trace, it's on the different routers that you're doing that. I suppose I can just do a trace route. And this is just on all the different routers, seeing how traffic and the ping and the trace route works. So you can spend time on that. We're just going to run out of time if I don't continue. So for our next lab, we're going to have to remove that global block that's been assigned to all our routers and then give them their own segment of that global block. So as mentioned already, we're going to create our relative SID index of a number based on our router. So router 6 is going to be 600. Router 1 is going to be 100. Then we're allocating each of our routers 1,000 of those addresses, labels that we can use. So this is the example that we've got here in the topology. I'll just minimize that so I can come back to that later on. So we're going to get out of the Zoom. Go to our router 1, go into the config terminal, and we're going to modify what's already there. So if we have a look at the helps if I can see our configuration that we had for so we've got our MPLS traffic engineering tunnels. Once that's enabled, we don't need to go back to it, but we can see here we've got our segment routing information. So we need to go in and remove our global block and then update our address family SID mapping to use a relative rather than absolute. So we go into our segment routing MPLS area. We're going to then turn off our global block using the no statement. We're going to re-enable it, but now we're finishing at 16,999. And then this will be different for each of our routers. We go into that prefix SID map. We then go into the address family. And then we turn off that absolute value. And we enable the index for that interface or for that prefix. So we're saying index of 100. We can save that out and write it. And the idea is that you're going to have to, depending on your device, you may have to reload your router to clear out the previous segment routing global block. So be careful with that. So in Cisco equipment or Cisco world, that's the easiest way to clear out that. Otherwise, it's not going to release that information. So to do that, we just do a reload. So make sure you have done a write command, and I'll let that run. So you'll need to do this for all of your routers. So I will wait for you to do at least router 1 and wait for you to come back for that. Let me know by typing in yes in the window. So essentially, we're going in, removing the sRGB, adding in an updated version of the sRGB, removing the absolute SID value, and adding in an index value instead for that prefix. So how's everyone going? Can I get you to say yes, you've done router 1? I'm just going to start on the other routers because I'll run out of time if I've got to restart each one and wait for them. So while that's restarting, I'll go to router 2.
I'm going to take off, sir.
So just to show you here, what you've essentially done when you're doing it on the other 4 or 5 routers is that you're setting up the going into segment routing MPLS area, you're turning off your global block, you're enabling the global block again, but just for the 1,000 rather than the 8,000. Then you're doing the going into the connected prefix location, the address family for IPv4, removing the absolute value and adding in index value. And then reload of the router. Did I do it right? Yes, I did. So while that's reloading, I'm going to go to router 3. It's too slow. So once you've done router 1, if you can do the other routers and get them reloaded, that would be good. And then once we've reloaded, it will just take a short time for it to converge. And once it's converged, we can go have a look at see how it's allocated labels. Are there any questions at this point? So that's done. Did I do a reload? I did. Okay, so now that's reloading. If we go to our router 1, I might just check the other routers have finished loading properly. Yep, that's there. Still loading. So, router 4, still loading. Router 5. Yep, we're getting there. They're just a little bit slow to load. So while we're waiting for those to finish loading up and to converge, I'm just going to go back to the original slide deck and continue with a little bit of the theory. So in regards to the MPLS, the example that we talked about before the first break, you're going to have this VPN label associated. At this point, we haven't got that. We've just built up our labels. But if you think about that example, we have this service label exchange. So we've got information that's coming from our destination to our source to be able to say, hey, if you want to get to me, use this label. And all examples for that service label will use that 1, 2, 3, 4. So our first example that we did in the lab configuration, we basically used the OSPF shortest path. So when I sent my trace route and my ping, my path from router 1, if I chose which interface to send it out, went, say, from router 2 down to router 5 and then up to router 6. So it did a zigzag approach. Someone else, it just did the bottom path. And so what we're doing there is that we built up this segment routing global block where everyone had the same segment routing. We had individual node SIDs, but we didn't have any adjacency SIDs. We didn't have any anycast SIDs. And we allocated an absolute value to those node SIDs. So everyone knew what 16,001 meant, and that was to send it to router 1. Everyone knew what 16,006 was for, and that was to send to router 6. So if we look at that from this diagram here, we've got our allocated information. We all got the segment routing global block of being 100 to 500. We've allocated our values for the nodes, which is in this case, P1 is 101, P2 is 102, P3 103, P4 104, 5 is 105, 6 is 106, and our exit nodes, our perimeter edge, provider edge was 111 and 222, and they're globally unique. And obviously they all have a prefix associated with that. So when we're building up our environment from this, we're using routing of the shortest path, so OSPF, using the typical shortest path. We're using our SIDs or segment identifiers as our nodes. We've got a label of an absolute value for each of our nodes, and we're using the same segment routing global block. So if I wanted to deliver traffic between the provider edge, it's going to use the shortest path. And if you see the metric here of 100, obviously that's going to add and make that link not a viable option for our OSPF. So in theory, it should go that way. So we've got 10, 10, 10, and 10. we can also build out our ILM from this. So when we have our ILM, it's going to start sending information to everyone. So provider edge 2 is going to tell the world about itself and say, hey, if you want to get to me, my label is 222. So router 3 gets that information and goes, okay, anything I need to send to the provider edge 2 is going to have the label of 222. And we saw those examples when we looked at our show MPLS forwarding table and so on. So it's going to build that up. And you can see that the router 6 has the same label information as router 3 to get to the PE2. Router 2 also has the same label information, but it has a separate interface to get to that. Router 5 will also get that information, but it won't most likely send it out that interface to router 6. Why is that? Because the metric is too high. So if you see, it's going to still have that information about in label, but to PE2, it's not going to send it out this interface to PE6. It's going to send it the lower value. So the metric is too high, so it's not going to use this link at all. It will send it to a lower cost path. Router 1 gets the same information. Router 4 gets the same information, and it's going to send there. So currently at this point, it's 10, 10, 10, 10. So that would be equal. But then you've got 10 extra there. So in theory, this will become our shortest path because of the costing. So now that we get our traffic forwarding, same sort of concept as what we saw for the MPLS. Our payload comes in. We then look up where is it destined to. If it's destined to PE2, we know that it has the VPN. So we add that service label of 1234, but we also put in the label that we know for this router over here, and that is 222. It receives that. Now we're sending it to router 1. Router 1 looks up its incoming label, which is 222. And the previous slide, we saw what the outgoing label was, which was 222. So it's going to swap 222 for 222 and then send it out the interface to router 2. Router 2 receives that information and it's going to look at its information, MPLS forwarding table, and go, I've received an in label of 222. I replace it with an out label of 222, and it goes out the interface to router 3. So off it goes. I now get to router 3, and if I'm not using penultimate hop, I'm going to do the swap again. So I look at my incoming and my outgoing, and I see it's 222 incoming. So the label I need to put on it is 222. So I swap that, and then I send it to my provider edge. My provider edge looks at 222 and goes, what do I do with that? I take it off. I look at my service label, which is 1234, and I need to pop that as well. So I take that off, and now I can send it to the customer. So the concept of MPLS is important because it's still using this label switching. The way that the labels are allocated is what's different from that point of view. So what we're looking at doing now is doing a similar concept. So this is lab 2, where we're still using the shortest path routing. We're still allocating our SIDs to our nodes, but we're using an index value rather than an absolute value. And we've got different global block addressing. So different labels for each of our routers. We'll see how that looks shortly. So in theory, that should be up. So let's go back to the instructions. Let's go to router 1. Just like what we did in the first lab, we're going to have a look at what label range we have active on this router. So active on this router, we have the label range of 16,000 to 16,999. If we go to router 2, it should be different. So let's go to router 2. So on router 2, we've got our label ranges being 17,000 to 17,999. So we can see that there is a different segment routing global block for our different routers. What about our forwarding table? What does that show us? Let's have a look at router 1. So for our forwarding table, we're going to see our locally significant value for our label. So on the left-hand side, we can see everything starting with 16,000 is significant to router 1 at this point because of that global block. So anything here is from my range that I had assigned from my local global block address. But you'll now see that I see other values there as well. So 17, 18 are examples. So 17 is from the sRGB for router 2. Not picking up my pen very well there. The 1804 is from router 3. Okay, so we still have the same local label, outgoing label, and the prefix associated with it, the outgoing interface, and the next hop. So from this, we can see that this sRGB, even though we're assigning it locally, it's advertised to the world. So router 2 through to 6 all know what this value label means. Unlike the other example with MPLS, where it's not globally significant, it's locally significant. The other thing that you will see is that my index value is gone 200, 300, 400, 500, 600. So it's gone up by 100. What was my index value? 100. Let's have a look at router 2. I'll just clear this pen. What do we see here? We've got our local label, we've got outgoing, we've got our all the same information as before, but you can see that my numbering system for the local label is 17,000, but it starts at 100, then it goes to 300, then 400, then 500 and 600. Okay, so remembering that that index value I'm picking up are from my neighbors. So router 3 has told me that its index value was 300. Router 1 has told me the index value is 100. Router 4 has said 400. So I'm giving a different label based on what the routers had told me their index value being. Let's go back to router 1. And let's have a look at our LSPF database and see what information we get from that. And so in this information here, we've got our advertising router ID. We've got our traffic engineering information with the segment routing algorithm that we're using. We've got our label information, so 16,000 for router 1. Range size, it tells us, is 1,000, so it's not as big as our previous lab example. And it tells us a little bit about the shortest path first algorithm and builds out from there, the neighboring routers and so on. So we can test the connectivity using the ping and the trace route. Let's see what happens with that. So it's getting you to test it for the other routers. Just going to scroll down. Otherwise, we're going to run out of time. I'm on router 1. So what we're going to do now is do the details for router 6, see what sort of information that we get from that. So we know that we've got our 2 paths. We've got the label 17600 going out to router 2, and then 18600 going out to router 3. Let's test which way it goes. So I'm not going to do a Ceph. I'm not going to do a ping. We've seen that example before. But let's do a trace route and see what happens with our trace route. Which way does it go? So in this case here, I've centered out my interface for gigabit Ethernet 1. So that's my next hop is router 2. So it's gone from router 1 to router 2. But now I have 18 and 38. So what does that mean? Let's have a look at our network topology and figure out where it's going from there. Just going to scroll up. Get my annotation. So in this case, it's gone from 1 to 2, but instead of going down to 10, it's gone from 2 to 18. So it's gone this way, and then from 18 down to 38. So it's taken just the top path. So 10, 10, 10, instead of doing the zigzag like the previous lab. But again, that comes back to how the conversions went, even though it costs the same. So at this point, it's really not too different to MPLS. It's using the label switching, it's using the shortest path. Any questions about that? So giving you the theory behind what we just did, we've got our same topology as what we had in the previous example that I talked about. Only difference is that we've got our sRGB is unique to each of our routers, and we've got an index value unique to our, or relative to our routers. Same concept of using the shortest path and nodes only. We're using a relative index and each have a different label range to choose from. We want to get traffic from 1 to 2 using the shortest IGP. So in theory, it should be the top one again. So it builds out the ILM, the same sort of process as before. The edge router is going to tell the world about its labels, and its labels are going to be using the index of 22, starting at 800. So that means 822. Let's tell the world. It tells the world what its index is. In this case, it's 22. And it also tells it the 822 for its label that it wants the world to know about. So router 3 goes, okay, so you're 822. Let's look up my sRGB. And you've also told me the index value of you is 22. So I'm 400. So let's add those together. And I now get a label of 422. That's what I've got here. I now tell the world to get to the perimeter edge 2 router. The label that you need to tell me is 422. So I then advertise that to my adjacency. For PE2, it's also told its adjacency about its label, and the same process of what router 3 did, looking at the index value and adding it to my global block to come up with a label unique to identify how to send traffic to that edge router. Router 2 does the same with the information that it learnt from router 3, and it does sets up the label. It also knows about that index value that's getting sent through with that advertised information. I now get that label of 322, and I tell router 5 and router 1 about that information. Router 6 is also going to be telling router 5 about how to get to that location as well. But essentially, we're building up the ILM, and it's specifying how to get to that. Okay, so we can see here that I've got the advertisement going down here of 322. It's given a label of 622. Told router 4 sees the label of 622, allocates 522 to it. Router 2 tells router 1 322, gives it 222, and eventually PE1 should be told how to get to the other side. So we've got this build up happening there. So the traffic forwarding, in theory, should go similar to what we saw. Payload comes in, we add the VPN label, we add the 222, which is the label that is unique here. So in theory, we should have 222 added at this point. We should have 322 added at this point, 422 at this point, and then 822 at that point. Let's see if that's correct. Payload comes in, we push the VPN or service label on and the label 222 and send that to router 1 because it knows what 222 means. Router 1 is going to swap that 222 with 322 because that's what router 2 said to do. It knows what to do with that label. Router 2 receives that and it takes off its incoming label and puts the outgoing label of 422 and sends that off to router 3. Router 3 takes off the 422 and swaps that with the label that it learnt from PE2 and sends that to PE2. PE2 is directly connected to the customer, so it pops both those labels and sends the payload to the customer. Any questions about that? So at no point have we done any traffic engineering apart from creating these labels. We're still relying on the routing protocol, the underlying routing protocol, to come up the shortest path algorithm. So now we want to start doing some sort of traffic engineering. So example with the traffic engineering, if we just use the node SIDs, so the information that we have allocated to each of these devices, we could potentially build up this segment list. With that segment list, we can then build up how we're going to send the traffic. Now, in this example here, they're going to have exactly the same segment routing global block information. We're allocating an absolute value as another example. So we've done that in lab 1. So you know roughly how to configure that. Here's the example. We've got the range for our sRGB of 100 to 499. Each one has been allocated an absolute SID, similar to our first example. Only difference is that instead of relying on the shortest path, we're using traffic engineering. If we have an objective of that all the traffic that is destined from PE1 to PE2, it needs to avoid that link, that node. Oh no, sorry, it should traverse. I should read the question, the objective. Let's get rid of that. So it must go through this node, but it can't go through this link. So it needs to always go there. So maybe go up this way, go down here, and across like that. Just like we can see there. So how are we going to do that? Well, we need to come up with some sort of list. What are we going to be traveling through? So we need to come up, obviously, and tell the world about all our labels. So the same process happens from the OSPF point of view. Go tell the world how to get to me. I'm going to share all that ILM information through to everyone. But in this case here, I'm advertising it with that label to the appropriate areas. But what I will also build up is this major informational list. So I now have this global list of anything with the label 222, it's going to have the out label of 222. And we've got that for all of our absolute values that we've set. And we're going to look for these exit values. Now we can see here that everything for 22 is going to be going to there. Anything for others are going to go out to P2. 103 is local, and 106 is going to go to P2, and so on. So let's look at it from a traffic forwarding point of view. We've got our payload that comes in. We're going to add not only the first hop label and the service VPN, but the path that we want them to take. So we've got one, two, three, four. Then we've got a label of 102. Let me just get rid of that. It's just a bit slow. Okay. So we've got the label. Oh, it's probably come up better if I just do that. So we've got our label of our 1, 2, 3, 4. And then our destination label, which is 22. So we've got our service, destination. Then we've got our router 5. So we basically build it up from the reverse. So we want to connect to our VPN. To get to our VPN, we've got to go to PE2, and then we need to avoid this link. So the way to avoid that link is to go to down here, which is P5, and then to send it a specific way, so it has to go through P2, we specify P2. That's essentially what we're saying here. So the first hop that we want, we don't need to be specific and say, go to router 1. We're just saying, go to 102, which is this label here. Now, obviously, with this traffic engineered, it's still going to rely a little bit on the shortest path. So going down this way is 3 hops. Going this way and going that way is 2 hops. So it's still going to rely a little bit on that shortest path information. So now that we've got this stack or this segment list, that information gets sent through to router 1. Router 1 looks at the incoming top label. In this case, it's 102, and that's all the same no matter which router you're on. So it's going to have exactly the same label for outgoing. So it swaps 102 with 102 and sends it on to router 2. Router 2 looks up its label information for that, and because it's local, it pops it. It doesn't need to keep that on there. So it takes off that top label of 102 and then sends it out to the next label. In this case, 105. So it looks up 105 in its table and it sends that out to its router 5. Router 5 receives that information and it says, hold on, the top label is me. Let's remove that off. Looks up 222 in its routing table, replaces it with 222 and sends that out to P6. P6 looks at that, 222, replaces it with its outgoing label of 222 and sends that out to PE2. PE2 is directly connected to the customer, so it pops those two information like that. Any questions about that? That's essentially what you're trying to do with this segment routing, is that you create this segment list like that. With that segment list, it uses those labels for you to then direct the traffic from the source to the destination. And we can get more complex than that, but we've sort of run out of time. Are there any questions? Now, I think with the lab environment, we've got to the point of creating a simple label stack and experimenting with different labels or segment blocks. So what you can do now is task 3 is what I just talked about with the traffic engineering and being able to go through and create an explicit tunnel to send your traffic. So you can do that after the event. And in this case here, it's still using the separate address and the relative index. And so that would have been my next use case, which is this one here. And we can also build up things like having your node SID and your adjacency SIDs to be able to then specify which links to use rather than a node. So if we look at this example here, we want to basically build up traffic going from PE1 to PE2 has to traverse this router, but avoid this link, just like previously. But notice the cost is a metric of 100. So we're still going to force it through there. Because if we'd done the previous example of the traffic engineering, where we had the label going to 102, then 105, and we had a metric of 100, OSPF would most likely send it back this way. Okay. Building our ILM, we now need to add some extra information because we're adding in the adjacencies into this location, into the label. So let's advertise that information. So we go through, send out our labels to everyone. And you can see here for router 5, I'm going to have the labels 222 and 106 are all going to have a cheaper metric, because remember, if this was 10, 10, 10, 10, 1, 2, 3, 4, that's 40 compared to 100, which is, even though I'm physically connected, it's going to be cost-wise cheaper to send it around this location here. So that's going to be an issue. So what I then need to do is have a separate label to specify my adjacency. So in this case, the label 1001 specifies send it out to P6, that adjacency SID. I also have the labels for the other locations, and I advertise that as well. So from everyone's point of view, you're going to build out this listing of your in labels, your out labels, and which interfaces you're going to send it towards. From the traffic forwarding point of view, let's send our payload to our provider edge 1. Provider edge 1 is going to put what labels on there. we've got our service labels. Those service labels then going to have the destination label, which is 222, but it's going to have an adjacency label in there as well. So we still have our router 2 and router 5 SIDs, but we've added in this adjacency SID as well to force the traffic over that link, even though the metric is higher. So we still build out the stack just like what we did in the previous example. So 1002 is our router 2 next hop, so it goes there. So when router 1 gets it, looks up the incoming and outgoing label and swaps it. Router 2 sees the incoming label is the same as itself, so it removes that, looks at the 105 label and the incoming and outgoing and sends that out. So it pops 102, sends it out to router 5 pops 105, as well as the adjacency link, because that's local to itself. And then it sends it out to that interface, which sends it to router 6. So it now gets to router 6. Router 6 swaps it, and it gets to the provider edge. The provider edge pops off those 2 labels and sends it to the customer. Any questions about that? So I've gone over by about 10 minutes. Does anyone want me to go through one more use case? And in this case, this is for the Anycast segment. I don't want to utilize everyone's time.
Yeah, Warren, we're already, I think, 9 minutes past.
Okay, so we'll finish there. So thank you for your time. Segment routing is a broad concept. We just started to touch on the tip of the iceberg. I found if you do the practical side, it may help with the theory. I hope it did. And using the diagrams and understanding the labels and how they get built and then sent and shared through your network is important. So you have node SIDs, adjacency SIDs, Anycast SIDs. You've got your segment routing global block, and that information is shared between the routers on your network. Hopefully it has been informative and you learned something. Feel free to send us questions. If you want more information, you can always contact us. I'm just trying to find the wiki page. So in here, there's some contact details there. There is also a shared document there if you want to experiment with the lab and see how you go. And if there's any errors, you can go into this Word document. I'll check that next week for you.
Warren, there is a question from ASM Mahabub. He is doing a lab, so he wants to continue with the lab. So is it possible?
Yes. So this virtual academy, I end up doing it this way for the fact that you can start and stop this as many times as you want. And you'll see here, it allocated me 2 hours, but I can always extend it. It'll pop up a message like this saying, you've got less than 20 minutes left. Would you like to extend it? I click on yes. That will automatically extend my time by an hour. But what I can do, if I click on this hamburger here, I can save this and it will save that virtual machine or all these routers for up to 7 days. And you can come back at any time and experiment with that. If I press end, that's going to end my lab. And I just go cancel, or you can do end, mark it as complete. It's up to you. And I click on OK, and that frees up my allocation to do another virtual lab or come back and start this virtual lab again. The only limitation with the Academy is that you can only have one virtual lab signed out at a time. So I hope that helps.
I think there is no question. Not seeing anyone.
No, I don't think there is.
Okay.
But normally we deliver this segment routing over a full day if we're doing face-to-face rather than just a couple of hours.
I think, Warren, so we can call it today.
Yep.
So thank you, Warren. Thank you, Zubair and Tashi. We all know that it's a very big topic. You know, one day or like 4 hours is not possible to complete all the things. And also, I think lab is very important. You try to show so many things. I think, and if people join the lab in the Ethnic Academy, I think they will easily find out how to go forward. And also, this video is already uploaded to YouTube. If anyone wants to see that one, go back and recap, so you can do it. So thank you, Warren. Thank you, Zubair and Tashi. You are a nice trio, I should say. So next time, I guess probably we will do a face-to-face workshop regarding segment routing, probably for 4 days or 5 days.
I hope so. I miss Bangladesh. All the noisy cars.
we miss you as well, Warren bhai.
So thank you everyone. আর অন্যান্য সবাইকে বলছি কালকে আমাদের কনফারেন্স ডে। কালকে আমাদের কনফারেন্স শুরু হবে 10টা থেকে আবার সেই দুপুর 2টো পর্যন্ত। কালকে আমাদের 4টা টেকনিক্যাল প্রেজেন্টেশন আছে এবং 2টো কিনোট স্পিচ আছে এবং 2টো কিনোট স্পিচই খুব সুন্দর। আশা করি সবাই আপনারা জয়েন করবেন। সবার সাথে কালকে দেখা হবে। থ্যাংক ইউ এন্ড খোদা হাফেজ। Thank you, Warren. Goodbye. Goodbye, Zubair.
Bye.